Good morning, one and all, and welcome to the second day of the 3 days international conference on graph labeling and application. For the first session of today, we have Dr. Kiran R. Bhutani who will be chairing the session. She is Professor and Michael Gudehi Chair of the Mathematics Chair, Department of Mathematics at the Catholic University of America. She completed her PhD in the year 1983 from McMaster University, Hamilton, Ontario, Canada. Her thesis title was Abelian groups in a topos of sheaves on a locale. She has a rich teaching experience to her credit. Her current research interests include graph theory, application of graph theory to theoretical computer science, data science, networks, security, and distributed computing, fuzzy theory, and its application. She has published a book titled Fuzzy Group Theory, the authors of which being John Maudison, Kiran R. Bhutani, and Asriel Rosenfeld. She has richly contributed to research in terms of paper publications. Her recent presentations include On Average Measures in Polymorph Graphs, a talk presented at the Conference on Emerging Trends in Graph Theory, Christ, deemed to be University Bangalore, India, in February 27 to 28, 2020. On F domination in graphs, talk presented at the 49th Southeastern International Conference on Combinatorics, Graph Theory and Computing, March 5th to 9th, 2018, Florida Atlantic University. A study of domination-related parameters in graphs and their applications, a talk presented at the 48th Southeastern International Conference on Combinatorics, Graph Theory and Computing, March 6 to 10, 2017, Florida Atlantic University. She has a book chapter on the paper Dissimilarity Measures between Fuzzy Sets of Fuzzy Structures. This paper has appeared as chapter 5 in the book Soft Computing Approach to Pattern Recognition and Image Processing, series in Machine Perception, Artificial Intelligence, Volume 53, published by World Scientific 2002. She is also an associate editor of the journal Intelligent Automation and Soft Computing AutoSoft Press, Albuquerque, New Mexico, USA. She has been invited to serve on the math panel and has chaired it twice for evaluating applications to the National Defense Science and Engineering Graduate Fellowship Programs 1997-98, 2000 to 2008. She has been a referee for the following journals: IEEE Transactions on Fuzzy Systems, Pattern Recognition Letters, Information Sciences, Journal of Fuzzy Mathematics, Iranian Journal of Sciences, Integers Journal, Intelligent Automation and Soft Computing, Journal of Approximate Reasoning, Indian Journal of Pure and Applied Mathematics, published by the Indian National Science Academy. She is a member of the Committee on Appointments and Promotions in the School of Arts and Science at CUA. She is a member of the Academic Senate at the Catholic University of America. We welcome you amongst us, ma'am, and I request you to take over.
Madam, please unmute your mic.
Thank you. Thank you, Stephanie. I am delighted and honored to be invited to the conference held in loving memory of our dear Professor B.D. Acharya. I also want to thank the Department of Mathematics, Goa University, and the organizing committee for arranging this wonderful conference. It is now my pleasure and honor to introduce our next speaker, Dr. Jay Baga, who's Professor of Computer Science at Ball State University in Muncie, Indiana. His research areas include graph theory, graph algorithms, theoretical computer science, and applications. His extensive research has been supported by federal, state, industry, and university grants totaling more than $5 million. As applied to network integrity, his research in graph theory has led to the discovery of efficient algorithms for creating communication and other types of networks that are less susceptible to disruption. Dr. Baga was a senior US Fulbright scholar at the University of Zimbabwe. Besides his research activities there, he developed the curriculum for a new computer science graduate program. He is the recipient of the Ball State University's Researcher of the Year Award which was distinguished not only by his investigations in graph theory and graph algorithms, but also by his productive international research activity and promoting exchange of ideas. In addition, Professor Baga is actively involved in the state of Indiana Voting Systems Technical Oversight Program, and as a co director of this program, he has worked with a committee that organizes the state certification testing of voting systems to discuss ways to improve the reliability of voting systems to uphold the integrity of the vote for the American electorate. I can go on and speak about Dr. Baga, but I think I should stop here and give Professor Baga a chance now to start with his lecture on graceful unicyclic graphs, old and new result. Professor Baga?
Thank you very much, Professor Bhutani, for that generous introduction. I would like to begin by thanking the organizers, especially the organizing committee. And it's been a pleasure to be part of this in honor of Professor Acharya, and whom I had met several times. So I'm going to be talking about graceful unicyclic graphs. Let me share my screen here. So I hope you can see my screen, the first slide. I'm going to maximize it. Can everyone see that? Okay.
No,
so
we can't see.
You cannot see the screen?
At least I can't see.
No, we cannot see it.
Okay. Let me see why it's not sharing. Okay, now it should be, you should be able to see it. How about now?
Not yet for me.
Not yet.
Now,
Do you have sharing enabled? Do you have it enabled, Jay?
I thought I did. Let me see.
Yes, now we can see it.
Yeah, so there is another button that I should have clicked, which I have now. So you can see my Acrobat and the first screen. So this is some old and some new results on graceful unicyclic graphs. I've been involved in this research now for several years. And I got interested in this through a couple of my students who brought me this idea. And then we got some interesting results done on unicyclic graphs, and we discovered that there was a lot more that had been done and a lot yet to be done. So I would like to start by talking about my collaborators in this area of research. And they are an international group from many different countries. So Arumugam, of course, is part of many of these papers and research that we published, and he's from India. He doesn't need any introduction. He was the main speaker yesterday. Professor Fortso is a professor of computer science from Cameroon. And I was in Cameroon, Yaoundé, a few years ago. And she came to Ball State as an exchange scholar, and that's how our collaboration started. So she asked me to come do a workshop on graph algorithms and graph theory in Cameroon. And there I met Max Pambi, the other person listed. And with Max now we have several papers. Adrian Hines came from Argentina originally as a Fulbright student to Ball State University to do his master's degree. And then he got interested in graph theory and graph algorithms. And then he decided to stay and get his doctoral degree, Ball State's EDD, because he was also interested in educational technologies. So he worked in this area with me. And then Mahbubul Majumdar, also a student who came from Bangladesh, and he's the one who asked us to start looking at these unicyclic graceful graphs, who is now a professor of statistics. He got his PhD from Ames, Iowa State University. So a number of collaborators on different topics that we have worked with. So I will spend a lot of time on graceful labelings of unicyclic graphs, but I'll also talk about graceful labelings of other graphs a little bit. And then I'll talk about some properties of some unicyclic graph graceful labeling that we've been looking at. And in doing all that, we have also developed some algorithms, and those algorithms helped us generate a lot of graceful labelings, and then helped us find some of these properties that we may not have otherwise discovered. So we don't need much by way of definition, but I'll just go through this so that we are all on the same page, or if I may say, we are all on the same screen. So graph labeling is an assignment of integers to vertices or edges, or both, subject to certain conditions. And we generally start, this kind of labeling was introduced in 1960s, and since then, many different graph labeling techniques have been investigated. Of course, graph labelings have been around even before then, but the kind of labelings that we talk about in this area. So there is a survey by Gallian, which everybody knows about, and that the current edition of that survey from December of last year, I believe, has 2,800 some 20 something papers. So over 2,800 papers are listed in Gallian's survey, but maybe there are more. So that's that one, which you can easily find online. If you just type dynamic survey of graph labeling, you should be able to get the PDF. Since a lot of work has been done in trees, I also listed another reference. That's a somewhat older reference from 2006 on survey of graceful trees, but there have been quite a bit of other resources that you can find as you search on the web, on the internet. So let me go to the next slide. So we start by assigning labels to vertices 0 through q, where q is the size or the number of edges of the graph. And then each edge gets a corresponding label by taking the absolute value of the difference of the corresponding vertices on that edge. And we call this labeling graceful if then the edges also get labeled 1 through q. There are q edges and they get distinct labels 1 through q. And if such a labeling exists, then the graph itself is called graceful. So here is a graceful labeling of a unicyclic graph, and this graph has 32 vertices, and since it's unicyclic, it also has 32 edges. And since the vertices are labeled from 0 to 32, that's 33 different labels. One of the labels will be missing, and later on we'll talk about that, some properties of missing labels for some unicyclic graphs in particular cycles. So you will have a hard time finding out which label is missing, so I won't keep it a secret. The vertex label 18 is missing, so no vertex is labeled 18. The other vertices are labeled 0 through 32. And of course, the edges are labeled 1 through 32. And since 32 is an edge label, it's always true that the edge label 32 will have the two end vertices 0 and 32, because that's the only way you can get that edge label, and so on. So there's some other properties we'll use. So here's another example of a caterpillar which is gracefully labeled. So there's a well-known result, conjecture by Ringel and Kortzigs called Ringel-Kortzigs conjecture on trees, that all trees are graceful. This is, a lot of work has been done on this, but still an open problem. It's one of those diseases of graph theory sometimes that Frank Harari used to call these graph theory diseases, and this is one of those. That if you get infected, then you can't give it up. Then you keep trying to solve that problem. So of course, people have tried this with algorithms by brute force to try to find graceful labelings. So Allred and McKay back in '98 showed that all trees of order up to 27 are graceful, and they did that by an actual search, a structured search, backtracking and such. Now that result was extended for up to 35, order 35, by all these authors. And in doing so, there was a community of researchers using their computers in a cluster environment, and they helped work on some of these trees. Of course, there are special classes of trees which are known to be graceful and proven to be graceful. Among them are paths and caterpillars and many others.
Jay, can I ask you a question?
Uh-huh.
Do you believe the conjecture?
Yes.
Okay, thank you.
So back in 1948, from a paper in Annals of Math, these are the numbers of trees listed, number of unlabeled rootless trees of this size. So you can see the number of trees grow quickly. This lists up to 32. So it's a hard problem to do it by algorithms, by brute force. We do not have the computing resources to do it at this time. So this is a slide from a table from this paper by Wenji Fang archive. You can easily search for that. A computational approach to graceful tree conjecture. Archive published there in 2018. And so again, you see the numbers of trees from n equal to 20 all the way up to 35. And so with the backtracking algorithm, they were able to find graceful labeling. So all you have to do is to find one graceful labeling of each tree from that list of trees. And then a few of these could not be handled by backtracking. There's a hybrid approach they did, a little bit of probabilistic and structured algorithm. If you want, you can see the details in the paper. And here is the average time in microseconds that it takes to do these. So it's been estimated that for order beyond 35, it will take years to do each order. So I think that's the status of this problem. The last 3 rows here for 33 to 35 have been done, as I said, with a cluster of computers. So there is hundreds and perhaps thousands of computers working collaboratively to do different parts of this problem, and they were able to then get to up to 35. So I think that may be the most recent that we have. I looked for something beyond that. I haven't found it. If any of you know that, I would be interested in finding out. Anyway, that's all I want to say about trees, because that's not the main focus of this talk. I want to talk about unicyclic graphs. So Rosa back in 1967 showed that a cycle Cn is graceful if and only if n is congruent to 0 or 3 mod 4. He in fact proved a more general result for Eulerian graphs, and that's how he was able to do this. So he showed from that result of Eulerian graphs that cycles Cn when n is 1 or 2 mod 4 cannot be graceful. And then he gave actual labelings for cycles for n equal to 0 or 3 mod 4. And that's how he was able to get the result for all values of n. So by that constructive proof. So his result of Eulerian graphs, which is a little more general than cycles, would be that if G is an Eulerian graph with n edges, and n is congruent to 1 or 2 mod 4, then G cannot be graceful. And that's just a parity argument, essentially. All right. So by contradiction, if G were graceful, and if you label the edges 1 to n, then the sum of all the edges is that number, n choose 2, n plus 1 choose 2, and that is odd if n is 4k plus 1 or 4k plus 3, clearly. But on the other hand, if you look at any closed walk and you look at each edge on that closed walk, and since the label on the edge is an absolute difference of its, so it's AI minus AJ or AJ minus AI, it's the same parity. So if you add them all up, that number should be even. So therefore you get your contradiction right there. And hence a cycle of that order, n congruent to 1 or 2 mod 4 cannot be graceful. But then Rosa showed for n equal to 0 or 3 mod 4, he was able to actually construct. So the reason I'm showing this cycle, and this we computed with one of our algorithms that we wrote. This is a cycle, I believe, of order 19. 19 edges. And so the value 0 to n. And the colors are interesting. A green color is what I call a high label, which means that both the labels on either side of that green vertex have lower labels than the green. And then a red label is a low label. On both sides of a red label, you have green or other vertices are higher than that. And a amber label is a middle label, which is neither high or low. So one side is bigger and the other is small. And I picked these three colors, red, green, and based on the lights, street lights, which are, so I forget which is the highest light. I think the red is the highest. And then you have green at the lowest and amber in the middle. And so that helped me remember that red is high. So because then red, you want to be able to easily see. So the highest in a vertical, of course, on many streets in Muncie and other streets, nowadays they have horizontal lights, where the lights move left to right rather than up to down. But anyway, that's besides the point. So as you count these, we found some interesting properties of the high labels and the low labels and the intermediate labels that we'll talk about. So of course, since the result for cycles was done by Rosa, then people asked, what about other unicyclic graphs with exactly one cycle? And so Tuzinski conjectured in '84 that all unicyclic graphs, except the cycles which were forbidden by Rosa's result, n congruent to 1 or 2 mod 4, are graceful. So that's an open problem yet. Unicyclic graphs, except those cycles, are all graceful. So in solving this problem, people have looked at several classes of graceful unicyclic graphs. In most cases, people have looked at unicyclic graphs by constructing interesting unicyclic graphs. Unicyclic graphs is a very large class. And then they found that the class that they construct, they put some structure on it with it being unicyclic. So they're able to easily construct a graceful labeling. And so several such classes are known. And since the title of this talk is Old and New Results, I'll talk about some old results too, and then give some new results, more recent ones. But before I go to classes of other unicyclic graphs, let's just stay with the cycle for a minute. Because cycle are the simplest cases of unicyclic graphs. So this is a result. This is some results, some work that we did with our students. And then it got extended to other unicyclic graphs too. So we developed an algorithm. It's essentially a simple depth first search kind of algorithm, which looks at all of the possible labelings. Our goal is not to show that these are graceful, because we already know they are graceful. Cn, where n is congruent to 0 or 3 mod 4. Our goal is to list all the graceful labelings. Just find all the graceful labelings that are possible, and there's many. And so then we studied those and then look at some properties that they might have in common. So we discovered several graceful labelings and observed that they satisfy some interesting properties. So here I bring back that figure again. This was found by one of our algorithms, a graceful labeling of 19. So since a cycle it's a unicyclic graph, it has equal numbers of vertices and edges. So if you label it with 20 vertex labels, 0 through 19, one vertex label goes missing. And we saw that in the opening example also. So in this case, there is a missing label too. Of course, all the edge labels 1 through 19 are present. So out of the 20 vertex labels, in this particular example, the missing value is 9. So the label 9 is missing as a vertex label. And we were interested in seeing what kind of values will not be missing and what will be missing. So our data that we generated from our algorithms helped us find that. So let me talk about the algorithm a little bit, and then we will look at some data that we generated out of those. So of course, as we said earlier, the labels 0 and n have to be adjacent, because that's the only way you can get the edge label n. So we start with what we call level n as our search. So we, on a cycle, which is of course vertex transitive, any two vertices can be labeled 0 and n. So we do that, and then we try to see how we can get the edge label n minus 1, of course. Well, again, to get the edge label n minus 1, it will be a difference of n minus 1 and 0, or n and 1, and those are the only possibilities. And so since we already have n as a done vertex, we can place 1 next to n, or we can place n minus 1 next to 0. So now we have, so these strings of labels grow. So what happens is you get paths on the cycle. So to start with, you have the cycle, then you grow paths on the cycle. And these paths at times can be disjoint also. And then you go, so the level indicates the label of the edge. So the level n is the label of the edge, which is the difference, absolute difference, and so on. So in general, you'll have the level n minus k. And our algorithm proceeds in searching through this tree of labelings, and certain paths become dead because certain labels will not work. So then we quit that path and we keep going through other paths. Remember, our goal is to generate all possible labelings which are graceful, and that's why we do this. So this table indicates or displays the same idea. We start with n, which is n and 0, then n minus 1, and look at all the possibilities in decreasing order of the edge labels. Look at all possible differences. So now let's look at the general step of this algorithm. In the general step, you have already labeled from 0 and so on up to step k. And now you are looking at the next edge label. You are looking to find two labels for the next edge label E, which is the next step, such that you have two vertices labeled A and B with absolute value E. And A and B are not already in the set, or they are next to each other. And of course, A and B are less than equal to n. So I won't dwell on these conditions a lot. So my students, Adrian and Mahbubul, try to write out algorithms. So of course, to write an algorithm, you have to be careful that you covered all the conditions. So in general, you have these sub-labelings. You have A, B as part. And so this is really your cycle, and it's broken up into paths as you keep labeling. All right. So I won't again go into the detailed steps. So it keeps finding these labels, and at times you'll get stuck because you'll not have a choice for a graceful labeling. And then you just kill that path and keep going. So there are several possibilities to go. And again, I will not go into the details of the algorithm. This is a sample output of one of the algorithms for C8. So we start with 8, and you have 0, 8, and then 7, 0, 8, then 1, 7, and so on. And you can see how this proceeds. And eventually we may get a graceful labeling, or we may not, depending on how you label. So now, how do we know that in doing this, we will get all of the labelings? So we have to show correctness of this algorithm, which says that you give me a graceful labeling, I'll show that our algorithm generates it. And conversely, all of the labelings are generated, that this does not repeat. So there's a one-to-one correspondence between all labelings and all the graceful labelings that are there, and all the labelings that our algorithm generates. So that's a recursive or an inductive kind of proof that we can go through. And again, I will skip the details of the proof. And it turns out that it indeed works. So if you assume the general step, the recursive step, then you show that the next step follows. And here is a more diagrammatic way of looking at how our algorithm proceeds. There are different possibilities. So at any given time, you have labeled a part of the cycle, and you may have several segments on the cycle. And this is what I was saying. you actually generate paths on the cycle, and eventually all the paths close up to give you a labeling of the whole cycle. And if they don't close up, then you don't, that particular doesn't work. So then we ran this algorithm for up to order 16, and it took some time to run, and we were able to find all graceful labelings. Then we looked at what others had done, and it was known back in 1990, and our research is after that. It was known back then that graceful labelings of paths grow exponentially. That result was already known. I mean, the number of graceful labelings of paths. So there was a result of Aldred back in 2003, which said that for large n, the number of graceful labelings is at least 5/3 to the n. And so here is a table of some of these. Now here we are talking about paths, but paths and cycles aren't too far apart in terms of the growth of these labelings. So because you can remove a vertex and then carefully, and then you can see. We compared our algorithm with some other algorithms. There's an algorithm by Eshgi and Azimi in 2003. And their algorithm took these, and these are, I think, seconds for cycles of length 8, 15, 20, 50, to find one, and ours finds several. So we can find one very quickly in 0.01 second, we can do C, and so on. In fact, we can do, I think, most all the labelings. So we generated this data up for cycles of length up to 24. So of course, we are only allowed these numbers, 3, 4, 7, 8, 11, 12. Remember the numbers 1 or 2 mod 4 are forbidden by Rosa's result. So these values 3, 4, so on up to 24. And we found the total number of graceful labelings for each of those. So starting out with very small number of graceful labelings for cycles of length 16, there are 20,464 graceful labelings. And then it, as you can see, it grows quickly. At 24, there were 107,399,400 different graceful labelings that we found. And I still have all these stored somewhere on a hard drive, taking up lots and lots of space. But yes. But now look at the columns. So on the left side, we see M, which is the missing value. So we talked about the missing value before, and this was very illuminating, if I may say so. Because if you look at the missing numbers 0 through 20, we saw that, of course, it's trivial that 0 and 20 cannot be missing. That's the only way you can get the label 20. And then we saw that others may or may not be missing. So you can see that there's a symmetry about this table. So the top rows here are blank, cells are blank, and so are bottom cells. And most of the missing numbers are in the middle 2/3 values, right? So you can see the missing numbers for 24 are between 6 and 18. So for C24, these numbers 0 through 5 never can be missing. So missing label has to now. So that clearly led to some conjectures, and then we proved those conjectures. So without this data, I'm not sure we would have found that theorem. Another thing to note here, besides the missing labels, is the symmetry in the rows. So I have 5,932, this number for missing label 5 of C20. Well, at the bottom, you also have 5,000. And then you have 39,692 and 39. And so clearly this is symmetric, and that's easy to see, that we knew already. And in fact, this data confirmed that our algorithm was working, right? Because of the complementary labelings, right? So given a labeling, you can always have the complementary labeling. Just convert all by subtracting. So 0 becomes n, n becomes 0, and so on. So, and you get the edge differences stay the same. So then this is symmetric. So in the middle, of course, sorry?
Jay, there's a typo in the table.
Yes.
In the middle of column 23.
Uh-huh.
There's a 2 that should be a 3, or a 3 that should be a 2 right in the middle.
Uh, 3690, 3690, force, I don't
Five,
see.
5,252,000.
Yes.
And the next one is 5,253,000.
Yes, because those are they complementary here?
Well, they don't look complementary because they're
They
different
don't.
numbers.
Right. And but then, and that's 23, which is odd, right? So there's one in the middle. And so, yeah, I think you're right. That number should be the same. And so I'll correct that. 4633, those two should be the same as they are in other cases, 196.
Yeah, that's what I thought. Okay, thank
So
you.
that typo, thanks for catching that. You're right. And I think that 2 and 3 are the culprits. So one of them is the other. Okay, thank you. So this data then, so the results that we saw from this, we were able to show some of the things here. So we saw that exactly one label is missing, and the missing value in that example we saw earlier is M. So we define the set of high labels and the set of low labels and the set of intermediate labels, like I defined before. And so H is the set of high labels, L and I. And let small h be the sum of all the elements of high labels. And similarly, you define small l and small I. So the sets are the capital values and the lowercase values are the sum of those vertices labels. So clearly this is true. The sum of all the labels is n times n minus. And of course, there are n labels in all. So here you see the H, I, and L, H being the high labels, I being the intermediate labels, and N being the low labels. So it's easy to prove that H is equal to L, and that will be a good exercise for you to try to prove. And then you have the high labels and the low labels and the intermediate labels. And since the number of high labels is equal to the number of low labels, it is same as N minus the number of over 2. And then we can show that if you take the sum of all the high labels and subtract the sum of all the low labels, you get this. So these are kind of elementary results which follow from the labels. And if you sum over all the edges, you get, of course, 2h minus 2l is n times n plus 1 over 2, and that's n, and so on. So the missing label turns out then to be h minus 3l minus I, where you remember that these little h and li or the sums of those labels. And then we can get this inequality on H, L, and I, which I won't go through the proof of. It's an easy proof. And we can show then that the number of high labels and the number of low labels is bounded below by this number from all those. And then we can show that all the high labels have to start at about floor of 3n over 4. The high labels are indeed in the higher numbers, and the low labels are indeed in the lower numbers, as one would suspect. And then we also were able to show that the missing value always lies between a quarter of n roughly to 3/4 of n, based on all those. So that confirmed our the data that we had, and you already saw that. So those are interesting properties of graceful labelings for cycles, and some of this we have extended to other unicyclic graphs too. So again, there's the table, and yes, Tom, I still have that, so because this is a copy of the same slide, so we'll fix that typo. Okay, so let me move to the next part of the talk, where I'll talk about some of the known classes, but I think we are going to be running out of time here, right? So I'll finish up by saying that there are several classes of graphs that have been known to be graceful. And in these slides, we call them dragons and kites and olive trees and hairy cycles. And all of these classes have been shown to be graceful. So this is a very quick 1-minute survey of some of the old results in unicyclic graceful graphs. There was a student of Rosa up in Canada who showed that all of the 377 unicyclic graphs of order up to 9 are also graceful. So he did that by some. That was his master's thesis, by the way, back in 91. And then others have proved other kinds of unicyclic grasses graceful. So I will quickly skip through these. And I guess I'll end here with this, with the last slide. Some of our recent work, we have found some larger unicyclic graphs which are graceful, where if you remove an edge, you get a lobster and not a caterpillar. And so here are some classes. For example, if you take K1M-1 star and append a 4 cycle, we have shown that unicyclic graph to be graceful also. So let me end there, Kiran, with this last result. Thank you.
Sure. Okay. Thank you so much for this interesting talk. Does anyone have any questions?
I'd like to ask if there are any, and by the way, I do think this is an interesting talk, which could have been boring, but it's not at all. But I'd like to ask if there are any patterns you see to the particular types of phenomena in the graceful labelings.
Mm-hmm.
That's a very vague question, and I don't know.
It is a vague question, and no, it's hard to, because it's such a large class, the unicyclic graphs, as I said, and what the researchers have found is by adding suitable graphs appended to the vertices of the cycle, and those graphs are kinds of trees that they append. And if they keep them somewhat structured, so they have a way of going around all the vertices of the cycle and looking at those trees. And those are kind of constructed so that we have that structure, and we haven't really figured out what that structure is yet.
So an example of something that you found actually was about the numbers of high and low numbers.
Yes.
And the ranges
we have
that
extended, right. We have extended some of those results to some of graphs that you see here, and I might show you a result. Here is an example. So here is some data that we generated for graphs like KM1, M-1 plus C4, which is appended. So we saw similar results. So that does show some structure. This data was generated and we found some interesting values. And then we proved how are the positions of the central vertices in the star. So like the missing label we found in this particular diagram, if you take the vertex where the two graphs are appended, what kind of labels that can have. So there is some structure that we are finding. Now, there is some general results, not for unicyclic graphs, but for graphs in general about where the label 0 might be. Arumugam, I see, is here, and maybe he can bring us up to date on some recent results. People have looked at in any graceful graph, where can the label 0 be? What kind of properties a vertex should have to have the label 0? So that was a long-winded answer to your vague question, Tom. But hopefully I want
good answer. No, thank you. That's it's like, where can 0 be? That's just the sort of thing I'm asking about.
Yes, yes.
Thank you.
Thank you.
Thank you. Does anyone else have any questions? In that case, thank you, Professor Baga.
Thank you.
Jessica, who?
Yes, Natasha. Yes, Stephanie. Do we have any questions in the YouTube chats?
No, there are no questions asked by any of the participants. No?
Yes, we can hear you.
There are no questions asked by anybody, any participants on YouTube. So I think we can end with the session if nobody from the speakers or chair also have any questions.
Which means that my presentation was either too hard or too easy.
It was too good.
Too good. Too good.
Thank you, Professor Jay Baga, for your session, and also thank you to Dr. Kiran Bhutani for chairing the session. I now hand over to Professor Sanford to carry forward the next.
Thank you, Professor Stephanie. It is my pleasure to invite the chairperson for the next session. Professor Mukti Acharya is a professor of mathematics at the Delhi Technological University and specializes in the graph theory. Her main contributions are in SciGraph, graph spectra, graph labelings, and Petri nets. She completed her Masters of Science in Mathematics from PFU, University Moscow, in 1974 and went on to do her PhD in Mathematics from IIT Bombay in the year 1982. She was appointed as a visiting scientist at Mehta Research Institute, now Harish Chandra Research Institute at Allahabad, Uttar Pradesh, India. She joined IIT Delhi Department of Mathematics as a CSIR pool officer and then as a lecturer in NCERT, Delhi. In the year 1994, she joined Delhi College of Engineering, now Delhi Technological University, as an assistant professor. She was appointed as a professor in 2002 and later headed the Department of Mathematics at the same university till 2013. She currently works as an independent researcher and has several visiting faculty positions at Kalasalingam University and Christ University. She has guided 4 PhD students. She has 67 publications to her name. Besides these, she has also written articles and a book chapter on Petri nets, manufacturing and computer science. We welcome you, ma'am, and I request you to kindly take over.
Thank you very much. But anyway, there was no need to spend so many minutes. But anyway, it's a formality, you are going to complete it. So I think next lecture is by Professor Jaslavsky. So is he, ask him to get connected?
Yes, ma'am, he's online.
I'm here. Hello.
Good morning. Of course,
Good
for you
morning.
it is good night.
No, it is legally the morning, even though it's dark.
Yes, legally, because we are active. Okay, the time clock does not matter. So I invite Professor Jaslavsky for his invited talk. I will not take much time to introduce him because our present group knows him very well and he is very active in his research. And I was very happy yesterday to know his friendship with Dr. Acharya. And when I joined Mehta Research Institute in March 1976, so his name used to be in my ears every day. Okay, that is, we will be talking about his work. Dr. Acharya will be asking me to work on graph theory because I was not a person of graph theory. I was from OR. Okay, my thesis, MS thesis for MSc was in transportation problems. But later on, Dr. Acharya told, what you are doing only graph theory. So you start learning graph theory. And then I learned basically graph theory from Dr. Walikar, who came there as to MRI for the work. So my graph theory is not that I will follow some book and all other things. So I will hear lectures, go and find out and study, do the problems and all other things. Okay. So Professor, as I told, Professor Jaslavsky name, I'm very much acquaintance, and also I have interaction with him personally in 2008, 2010 and 2016. Okay, and hope in the near future, he will make a visit to India. We will be in a position to meet this one, not virtual meeting. And as I told that he is very active in research, and he also likes to help the research scholars and people who are working in graph theory. I just want to say that in last 1.5 years, he has papers with different authors from India. So I can say one group is from Kerala. Okay, one group is from South Asian University, and one group myself and Father Joseph, and they are from South Asian Deepa and the students, and one more is there. I don't know the names. But
NIT Suratkal.
Huh?
NIT Suratkal.
No, I'm not wrong. 1.5 years.
Yes, recently we wrote a paper published in the Discussions Mathematicae. Myself, Professor Rao, Professor Jaslavsky.
Oh,
my
very
student
glad,
Suresh
very
Dara.
glad, very glad. So
Yes.
no, Karnataka is forward. No, I'm we Karnataka two groups, and from Kerala, from Delhi. So with these few words, I welcome Professor Jaslavsky for his talk. Thank you, sir.
Well, I guess I should start.
Yes.
And that means that I have to figure out how to show you my screen, which is not too hard. Here we are. Okay. And now I have to, something is, what in the world is going on here? Oh, I see. Okay. Now I have to share screen. And the one, here we are. I think. Wait a minute, that's not it.
Yeah, it's starting to share.
Yes.
It's sharing the wrong thing.
Done,
Yes,
done.
we can see it,
Done,
sir.
done,
We
done.
can
you-
see it.
Yes.
Yes.
You're seeing my title?
Yes.
Yes.
Yes, sir.
Structure for sign graphs.
That explains it. Everyone except me could see the title. Okay. Well, that's good enough, I guess. Now, the question is how, oh, okay, I've got it. All right. Unaccustomed as I am to speaking from several thousand miles away, I will do my best. And you will see something very strange soon, but let's start with graphs and signed graphs. Well, if you don't know what a signed graph is, here's what a signed graph is. We put a sign on each edge. And the question is, does this belong in a meeting on graph labeling? And the answer is not really, but if you're nice about it, then it does. It's a completely different concept of labeling from what we've been talking about mostly. However, it's very interesting, and there are labeling aspects, but I will not talk about that because what I want to talk about is structure. What is a structure of signed graphs? So let's talk about structure of graphs. In signed graphs, first of all, what's fundamental? So before we talk about structure, the fundamental concept is that if you go around a circle, which is my name for a cycle, then you will get a positive product of signs, or in other words, an even number of negative edges. And a sign graph where every circle is positive is called balanced. This kind of sign graph acts like an ordinary graph. It's when you get unbalanced sign graphs that you get interesting. Now, how do you tell if a sign graph is balanced? Here's the structure. Unfortunately, if you look down at the diagram, which explains the theorem, you will see that it is backwards. And I don't know how to fix that, or I would have done it. So you can see the word cut. If you can read from right to left in English, you will be okay. I don't think I can, but I will try to help you. So here is a cut, and this is an example of Harari's balance theorem. That is, if the negative edges form a cut, then the sign graph is balanced. And the reason is easy. Every circle has to go back and forth an even number of times. Otherwise, it couldn't be closed. So that's how it gets to be balanced. However, then you have to prove the other direction. That's not too hard either. I should mention that this was anticipated by Koenig in the 1930s in his book on graph theory, but he did not have the full concept of signed graphs. And I think that's an important fact that Harari actually invented in 1953. Well, let's go on to the next slide. And then we're going to talk about structure. So what is structure? Well, there's connection kinds of structure. Connected components, I think everyone knows what a connected component is. That's a one connected component, or a graph that has only a single component is one connected. The next step is two connected graphs that has no two separation, but you might take a connected graph and break it up into its blocks, which are the two connected parts. I had a nice diagram here, but my text compiler said you cannot put this in, I'm dying. So I left it out, but I think everyone knows this. And there's a graph connecting the blocks to the cut points that separate them, which is the block cut point graph. And this tells you structural information about a graph. So if we go a little further, we can ask about a structure which comes from matroids, and that is, do two edges belong to a common circle? And the answer is yes, if and only if they are in the same block. So that is equivalent to being two connected. Well, that's going to change with signed graphs. So there's the theorem, but that's a very simple theorem. It's not that simple, it's pretty simple. The next step here is three connected components. And Tut has a decomposition where you look for two separations and you can split the graph at two separations. This is a very powerful theorem, which many people don't seem to know or use, but I found it very useful. And then there are various constructions and decompositions, which I will mention a couple of, but I can't really do too much. Another thing is structural property. Lovász classified all the graphs that have no two circles that are disjoint. In other words, any two circles have at least one common vertex. He published this when he was 16 years old, so we can all smile. He is well known to be very smart. Then there are other types of structure, which is where you look for forbidden subgraphs. And more specifically for the type of thing I'll talk about, forbidden minors. A minor means that you take a subgraph and then you contract some edges. So we have Kuratowski's theorem, which gives forbidden subgraphs for planarity, and Wagner's variation on the theorem for giving forbidden minors for planarity. And those are the two famous graphs, K5 and K33. And then there's another theorem, the theorem characterizing graphs that can be embedded in the projective plane. And there are the two versions for that also, the forbidden subgraph and forbidden minor characterizations. And there's so many of these that I've given you an idea of the kind of thing that I'm interested in this talk about structure. So let's talk about some signed graph structure. Well, first of all, there was Harari's balance theorem. And in fact, let's look at a bigger theorem, because if you look at the part 3, this is a third equivalent, which turns out to be quite useful as well. And all this is in his original paper. For each pair of vertices, every path between them has the same sign. And often that's a property that you use to show that a graph is not balanced by finding two different paths of different signs. So there's a little more to add to this. And as an easy consequence, you can say that the signed graph, sigma is my notation for a signed graph. I started writing graphs with capital Greek letters. I have forgotten why, but there was some reason. So, I remember why. It's a reason that isn't very good, and I won't tell it to you. So sigma is balanced if and only if every block is balanced. And the reason is that balance depends on signs of circles, and a circle is always inside a block. So you never have a circle going through two blocks. Every block has a property of balance or not, and that decides it for the graph. And there's the proof. Well, that is the proof. That's a very simple proof, but it's a good thing to know, because it means if you're interested in balance, you want to look at blocks. Well, now let's look at blocks. So let's look at a block. Here's a standard theorem of graph theory. A block could be K2. However, that's a very boring block, and I'm going to ignore it because it has no circles. If gamma is a block graph, a block itself, I shouldn't say block graph. If it's a graph that is a block, every edge is in a circle. And a corollary is if you have a balanced block in a signed graph, then every edge is in a positive circle. But this is really trivial. What happens when the signed graph gets interesting, which means not balanced? It turns out that you want to ask a question about negative circles. Negative circles are what distinguish signed graphs. And in fact, we can prove that every edge is contained in a negative circle in a signed graph. That is a structural property. So can I prove it? Yes, I can prove it. Oh, here's the proof. Now, if you can read this backwards, Here is a negative circle in red. I'm assuming this block is unbalanced, so there is a negative circle somewhere. Now, is my edge E in a negative circle? The E1 backwards is one possible position for the negative circle. Of course, it's for the edge. It's in the negative circle, so it's in a negative circle. Let's forget it. E2 is an edge that sticks out from the negative circle. By Menger's theorem, the other end of that edge has a path that connects it to the negative circle somewhere else. And now we have a theta graph, which is two circles with a common path. And one of the two circles we can make with edge E, either this one below or the other one above, has to be negative. And so the same thing with the other possible position of the edge. So in any case, our edge will be in a negative circle. Well, this is not so trivial. It's not hard, but it's not trivial. When I say trivial, I mean really trivial. Otherwise, it's easy. Okay, let's see if there's any more we can say about blocks and edges. How did I go the wrong way? Yes, I went the wrong way. Here's another question. Is every pair of edges in a common negative circle? Now, in a block and a graph, every pair of edges belongs to a common circle. Now, in a sign graph, we'll ask about a common negative circle. There is an exception. It's not always true. And I say almost a theorem because I have not finished the proof. In fact, I thought I proved this 100 years ago, but I seem not to have been born then, so I guess I didn't. So here is a picture of the exception. This is called a necklace of balanced blocks. Now, here's a block, and here's another block attached to it, and here's another block attached to it, and here's another block attached to it, and each of these blocks is balanced. If it's balanced, I can take it to be all positive. I won't explain that, but I want to take every block to be all positive, except the edges sticking out of one of these attachment vertices in one block. They should be negative, and then every circle that goes around here is negative, but every other circle that does not go all the way around is positive. So the positive circles live inside a block. The negative circles, a subblock I call it, because the whole graph is a block. The positive circles are inside a subblock, and the negative circles are the ones that go all the way around. If you take two edges in the same subblock, they will be in a positive circle together, but they may not be in a negative circle together. That gets complicated, and I won't go into that. But there is somewhere I have something about that, and there is a theorem, which this theorem is not if and only if. You notice I'm saying that if the graph is this unbalanced necklace, then I'm not going to promise you whether they are or are not in a common circle. That's more complicated. But this is the kind of theorem you'll get. It's much more complicated than the graph theorem. And that's where sign graphs get interesting. Well, let's move on. Another block. Every edge is contained in a positive circle. Oh no, it's not true. Here is an example. This edge E is the only negative edge in the whole graph. It cannot belong to a positive circle. Every other edge might belong to a positive circle. In fact, that's not so clear, but certainly not when it's the edge E. So I have to say that if there is such an edge, which I call a balancing edge, because when you take it out, the graph becomes balanced. If there is such an edge, I don't want to say anything, but if there is no such edge, then every edge is contained in a positive circle. Now, if there's no balancing edge, this graph might be unbalanced. It could be balanced, that's easy. It could be unbalanced, and yet I believe, it's a conjecture, that every edge is in a positive circle if the sign graph is unbalanced, and this is not easy. At least as far as I can tell, this is remarkably difficult. So I call it a conjecture. I don't dare say I have an almost proof either. So this shows you how complicated sign graphs can get. Here's another question. Is every pair of edges contained in a positive circle? let's see, we were just asking whether every edge is contained in a positive circle. Oh my, so let's assume that every edge is in a positive circle. Can we say that every pair of edges is in a positive circle? Now I claim that this is the exception because it's obvious that an edge in one subblock and a different subblock are not in a positive circle, so it's obviously an exception. But I think if this is not the case, then I could prove, I think, but it's a conjecture. So again, we have a complicated statement. By the way, what time do I end at? I just want to check. Can anyone tell me? I started at 50.
At 11.
At 1:30 my time. Okay, thank you. Yes, very good. Okay, there's plenty of time. He always says that. Okay, let's look at connection. What is connection in a sign graph? Well, we could just look at graph connection. But that's not interesting for sign graphs. You can certainly say that a sign graph is connected if the underlying graph is connected. But do you want to say something more sign graphic? Let's, again, talk about this common circle that's a kind of connection property. Focusing on the relationship between edges, two edges are in a common circle in a graph, of an ordinary graph, if and only if they're the same block. Now let's ask, what is the analog of a circle for a sign graph? It's not actually a circle. It's one of these three graphs, which you should read from left to right, from right to left. If you read from right to left, here is a positive circle. Here is, that word is any. It means two negative circles that are joined by a path, and the path can have any signs. The circles are negative, meaning, remember, that the product is negative, not that the edges are negative, but has an odd number of negative edges. And then here's another type, which is basically a simplified version of the middle type. And this type is also what we call a frame circuit. These are the analogs of circles in a signed graph, according to me. And the reason is it comes from matroid theory. Well, I'm not going to tell you about matroid theory, but this leads us to ask whether two edges belong to a common frame circuit. This is not so simple. Let's look at what that tells you about the sign graph. Here is a theorem about when two circles belong to a common frame circuit. I have to look now. I'll assume that my sign graph is connected, because if it's not, each connected component is separate. So let's look at a connected sign graph. Now you really have to read backwards. By the way, I can hold up the original diagrams and you can look at them. But if you're okay, let me know. If you're not okay, let me know. This is, notice the red part. The red outline shows you, oh, let's read this. This is balanced, B-A-L for balanced. Balanced. These are blocks. Here is a block, which is an isthmus. It's a single edge. It's K2. It's balanced. They're all balanced. Here is an unbalanced block. Here is an unbalanced block. Here is a balanced block that is between two unbalanced blocks. You just read from right to left. It says unbalanced, unbalanced, unbalanced. Oh, here is a balanced block and here's a balanced block. They are not between two unbalanced blocks. So actually we're making use of the block cut point structure here, although I'm not mentioning the cut points. And the red part encloses all the unbalanced blocks and the balanced blocks that are between unbalanced blocks. Those are that is a set. I call that the inner part of this graph. In the inner part, every two edges belong to a common frame circuit. In the outer part, every block is separate. And the edges within a block belong to a common frame circuit, but not edges in different blocks. So this is the structure that corresponds to the block structure of an ordinary graph when you're talking about sign graphs. It's much more complicated. It's important for matroid theory, which I won't go into, but it certainly leads to interesting sign graph questions. Well, let's see, maybe there's more on that. I have a sneaky feeling that there isn't, because there's too much to say. But let's talk about minors. Now, this is where we get into theorems like Kuratowski's theorem and Wagner's version. So a minor means a deletion and a contraction. You're allowed to delete edges and contract edges. In an ordinary graph, contracting an edge means you shrink it down to a single point. So the endpoints of the edge become the same. If anybody's not happy with that, you should yell at me. But you're probably familiar with that, and if not, it's simple. But in sine graphs, it's a little more complicated. Deleting is totally obvious. You delete. When you delete an edge, you don't take out any vertices. I don't want to take out vertices. When you contract an edge, first, you cannot contract a negative edge. You can only contract a positive edge. So here is an example which you can read from left to right, and for some reason, it's upside down. So that E is actually an upside down E. It's not a G. And here is the negative edge that I want to contract. So I'm explaining what you do. This negative edge at one endpoint has various edges of signs, positive and negative, connecting it to the rest of the graph. And I'm going to switch, which means I reverse all the signs at this vertex down here. So the E becomes positive. That left-hand edge that's red becomes positive. That next edge, which is solid and black, it was positive, it becomes negative, and so on. That's called switching the vertex. Once I've switched the vertex, I can contract the edge, and this is what I get. No signs change after the switching. This is contraction for sine graphs. If you want to know how I came up with that, well, it's another story entirely. It doesn't belong in this lecture. But I can prove that it's the right answer. Well, by showing you what it's good for. So it is good for something. There was a reason for it. So let's see. Once you have that idea, we can now talk about minors. And it turns out this was the right idea for some reasons, one of which is about planarity. Now, let's talk about planarity for graphs. Well, a graph can be drawn in the plane without crossings. That's planarity. And projective planarity for an ordinary graph, it's the same in the projective plane. I mentioned the theorem about that. But for sine graphs, that is not the same rule. It's a drawing without crossings, but there's an extra condition. To draw a sine graph in a surface, any surface. By the way, this one is the projective plane. Now, if you're familiar with a projective plane drawing like this, you know that each point on the boundary, so we have here, the projective plane is this solid inside, but I didn't want to hatch it because it doesn't necessarily have lots of edges of a graph. But we have a disk, and we look at the boundary of the disk. This point on the boundary is the same as this point over here, opposite. This point A on the boundary is the same as this point A. That's a backwards A, sorry. This A and this A are the same point. Just above that A is the same point as just below that A. That's what the arrows are telling you. And this B is the same as that B. And just above the B to the left is the same as below to the right. So if we go around the boundary, we come back to the starting point on the opposite side, but we turn out to be backwards. Let me explain this. Let's start at V. Oh, this is V2 over here. It's not even easy for me to read. Let's follow this red edge. The red edges are dashed. That's to help you remember it's negative. The solid edges are black. Those are positive edges. Those edges do not cross the boundary. Now let's cross the boundary. We go along towards A, and let's think of carrying a spear. So you're facing A, and your spearhead is a spearhead to the left, just like that arrow. Now you walk in here, but you have become left-right reversed. You are now made of the wrong parity of amino acids. They have their backwards rotation, and you can't actually eat regular food because you can't digest it. But the important thing is that your spear has reversed. You have done nothing. It's automatic. Your spear is reversed. Your whole orientation is backwards, and you come back to V4. And this is how a sine graph is supposed to be embedded in a surface. Let's start here at V2. Let's start at V4. Carry the spear leaning to the left. Go down here. whoops, then up here, and you're carrying the sphere leaning to the left, and you go out here across the boundary, your sphere is leaning to the left, and you come back here, your sphere is now leaning to the right. You haven't done anything, it just happened because of the universe is projective. And you come back to the starting point, but you are reversed, your sphere is leaning to the right. That's called orientation reversing. A negative circle has to reverse the orientation. That's the rule for sine graphs. A positive circle does not reverse orientation like this triangle. A negative circle like that's actually a triangle. It's a circle of length 3. This circle through A reverses orientation. So my sine graph has 2 negative edges and 5 positive edges. And this is a way it can be embedded in the projective plane. The same goes for any surface. Now you have orientable surfaces, so sine graphs won't be very interesting for orientable surfaces. But if you like non-orientable surfaces, then there are plenty of them. Well, a Klein bottle, by the way, is the next one. There is a theorem about this. The theorem is that there are 6 sine graphs which are forbidden as minors in order for a sine graph to be embedded in the projective plane. And these are the 6 sine graphs. Let's explain this. I actually drew diagrams of 2 of them, but let's start with the simple ones. K5 with all positive edges. You can't embed it in the plane, so you certainly can't embed it in the projective plane, according to the rule that I explained before. K33, it's the same thing. If you make it all positive, you can't embed it in the projective plane. This graph is really K2 bar, meaning no edges at all, with a negative loop at each endpoint, at each vertex. And that's a topological exception. Now here's something weird. The wheel with 4 spokes, 5 vertices. If you make it all negative, you cannot draw it in the projective plane. Don't ask me to explain that. I'm not sure I could explain why. Now here's phi 4 and psi 5, or if you prefer phi 4 and psi 5. I change my mind every 24 hours. Now let's look at these. These are interesting graphs because this graph is phi 4. You notice that there's a vertex with all the positive edges and all the negative edges. This comes from taking K5, making every edge positive except one edge, and contracting that one edge. That's what this is. So there's some relationship between this and the K5, but I can't really tell you what it is. But they are certainly related in some way. And C5 is related exactly the same way to K33. So in a sense, there are 3 fundamentally different sine graphs that are forbidden, a K5 type, a K33 type, 2 each. Then there's a topological thing, which is really not sine graphs, but topology. And there's this one, which I can't quite explain. And this is the complete list. I was very happy to prove that theorem. I wanted to prove a theorem like that. And so I was glad I could do it. It takes about 15 pages to prove it. So it takes work. However, I just followed the model of the Dirac-Schuster proof of Kuratowski's theorem. It's completely intuitive. You don't have to believe me, but it really is. Okay, so let's move on to another aspect of this. Let's talk about disjoint sine circles. Now I say positive or negative. I'm not going to be too specific because there's a whole variety of questions. Also, what does disjoint mean? You could be vertex disjoint or edge disjoint. Well, here is an actual theorem. It's the only theorem we have about this. No 2 vertex disjoint negative circles. This is like Lovász's theorem. No 2 vertex disjoint circles. But now we're talking about negative circles. If and only if sigma is balanced, there are no negative circles, or it is projective planar. So it was important to talk about projective planar sine graphs. Or it's minus K5, that means K5 with all negative edges, and the square brackets means something that I won't go into, some minor variation. Or you obtain from the preceding by 0, 1, and 2 sums to balance graphs balanced planar graphs, I should say. I left out something. Okay, what's a 0, 1, or 2 sum? It means that you combine the two graphs with no common vertices, separate components, or one common vertex, which becomes a cut vertex, or two common vertices. And so you have your basic graph. You take one of these three types here. Actually, these don't have to be planar graphs, because we're talking about not projective planar. Projective planar is a type here. But okay, so this is the right theorem. We take this main part, it's balanced or projective planar or the minus K5, and we can stick on balanced parts with two, 1, or 0 common vertices. And that's the complete list, if I haven't forgotten something, of the sign graphs that have no two vertex disjoint negative circles. This is not a simple theorem, and I'm very proud of my second PhD student, Dan Saletti, who did this. He's very good. He's doing a lot of high-powered work on sign graphs and generalizations. In fact, I don't understand most of what he's doing, but that's good. Well, there are other questions we could ask about vertex disjoint positive circles, or edge disjoint negative circles, or, well, here's problem 1. Does sigma contain we just talked about that one. So let's talk about another variation. Do no edge disjoint negative circles? I don't think anybody knows how to answer that question. How about problem 3? No vertex disjoint positive circles. It's not hard to figure out that if the graph is not a block, then you can reduce this to the problem when it is a block. That's easy. After that, I have no idea what to do. This is a wide open question. And to be honest, I don't even know how to start with this. I think these are pretty hard problems. I'm not so sure about edge disjoint. I actually have no idea how hard that is. I don't think it can be easy. I think problem 3 is similar to problem 1, which was solved, but harder. However, that's up to whoever solves it. Well, one more idea about structure. Suppose you don't want to require that two negative circles only can't have any common vertices, but you want to require that they have at least two common vertices. In other words, I'm not going to say that any two negative circles are not disjoint. I say they have at least two common vertices. There was actually a reason that this comes up in connection with a problem that I'm not going into. It's also a structural problem. So I'll call these quasi-balanced. So here I have a theorem that I was almost finished with, I believe. It's a structural characterization of these graphs, and I'm not going to tell you what it is because it's not finished, and I'm not finished with the statement even. And that's pretty much it. Here's some references for those who want to look at the slides. And thank you for everything, everybody.
She's not there.
Oh,
Apparently, I'm a little early finishing. We can ask about questions.
Any questions from the participants?
Ma'am, there are no questions from the participants. If there are any questions from the panel list, they can go ahead.
So, Professor Jaslavsky, I want to know what about you switch a vertex?
I'm sorry?
How you switch a vertex?
How do you switch a vertex? Okay, yes, let's go back. Here we are. Okay, actually, well, if everybody can see this diagram, it's okay. Can everybody see the diagram?
Yes, I can see.
Okay. Well, if you can see, I'm sure you're the typical viewer. Okay, so let's compare the first diagram with the second diagram. I've taken this vertex, which I did not label, but let's call it V, and I changed the sign of every edge incident to that vertex.
Okay.
If there was a loop at that vertex, I do not change the sign because it has two endpoints. But otherwise, I change this sign. Now, I can do this to several vertices. Switching is a very powerful tool because you can often simplify a signed graph problem by switching and make fewer negative edges, which makes the whole sign graph simpler. So I found that it's useful in at least half of what I do with sign graphs. Now, what it does is it changes the number of negative and positive edges. So if you're interested in those numbers, switching is bad, but it does not change the signs of circles. And if what you're doing depends on the signs of circles, then switching is very, very good. For instance, if I have an interesting positive circle, let's go back to a positive circle or a negative circle.
It is clear to me.
I'm sure it is, but I want to emphasize how useful. Do you have another question?
I have other question. What do you mean by quasi-balanced?
Oh, well, it means that if you have two negative circles, they must have at least two common vertices. Not just one, but two vertices in common. So there are no negative circles cannot be disjoint and they cannot have only a single vertex in common.
Okay. That is two cycles having an edge in common.
Not necessarily an edge. That's an interesting difference. They may have two vertices that are not adjacent.
Okay, it's clear. Okay. So that
I should have made a picture for that, but my compiler may have exploded, so I'm not sure it would be good. It turns out this is interesting because when you look at the, you will never have these two types of frame circuits. This is the sign graph that only has the first type of frame circuit, the positive circle. That's why it's interesting.
Thank you. It's very, very clear to me now.
Very good.
Thank you very much for your nice talk on sign graphs and giving some ideas for those who are working on sign graphs. Thank you very much.
Well, thank you all.
I wish you all the best and good health.
Yes, everybody should have good health.
Dr. Acharya, can I still ask a question?
Surely, welcome.
So Tom, how did you manage to get those mirror images? Was it on purpose of some of your figures?
I went to my office to make nice figures. My computer would not work. I can't make the figures on my laptop because I don't have the right programming. So I hand drew these figures and I use a document camera to show them in Zoom, and I did screenshots. I saved the screenshots, but all the screenshots came out backwards. So then I converted them to PDF, but my computer has no facility for a left-right flip in a PDF that's made from a PNG file, which was what the document camera gave me. So I was stuck. I think it's very funny, but it was annoying.
Right. So in the document camera process, somewhere they got flipped. It looks
that's
like
correct.
That way. Yes. I was wondering if you scanned them on a scanner or did you do a camera? Because it's kind of interesting. Or sometimes you may want to do that on purpose. So.
Well, if you do, I believe there's some control in Zoom that you can set to flip left to right.
Yes.
And if I had been sure where that was, I would have done it, but I wasn't sure. So I only finished this about 11:30. It's a half hour at 9 o'clock Indian time. So I didn't have time to fool around.
Anyway, thank you. That was interesting to unravel those figures. Yes.
So I have a question on slide 12.
12, okay. Here we are.
Oh no, sorry. I think it is before this. Contraction in signed graphs. Yes, this one. Yes. So the edge which is negative, on the top of it, there would be edges that there also, right? So we interchange the positive and negative below the edge E.
We pick a vertex at the endpoint of edge E to switch.
So, yes, so
You
that
could
would be
pick the other
anyone. Okay.
Anyone.
Anyone, okay.
In fact, you can switch any set of vertices you like as long as you get E to be positive. That's the only requirement.
So we don't need to do at both the endpoints of the edge E.
You can't, that's the one thing you cannot do. Because if you do it at both endpoints, then you're switching E twice and it will be negative again.
Negative again, okay. Yes. Thank you,
That's
sir.
a good question. That's important. That's the sort of thing that is confusing until you get it.
Thank you, sir.
Are there any other questions from the panelist?
No, not from my side of it.
Sanford,
Okay.
are there no questions on YouTube?
There are no questions from any of the participants on YouTube.
Okay.
Okay, so we come to an end of the session. I thank Professor Thomas Zaslavsky for joining us, and I also thank Professor Mukti Acharya for chairing the session.
Wish you all the best. Namaskara.
Thank you, ma'am.
Thank you.
ma'am. Thank you, sir.
Thank you.
I personally thank Professor Jaslavsky and Bogga and Professor Kiran Bhutani from the US is sparing a valuable times.
And during nights,
As well as given invited lectures.
yeah.
Yes, thank you very much, sir and ma'am, for accepting our invitation and giving us this honor of your presence for the conference. Thank you, Professor Jaslavsky. Thank you, Professor Bagga and Bhutani ma'am. Thank you very much.
Thank you all.
It's about 1:30 here. Tom, it's not your time yet. You are up till 6, but I think I'm going to call it a day.
Yes, sir. Yes. Thank you so much for your presence.
Happy
Thank you.
to be part of.
Thank you, ma'am. Yeah.
Have a good sleep.
I request Professor Bagga, I need your WhatsApp number actually. Somehow I misplaced because of the changing of the
Okay, I'll send it to you. I have yours, I think.
Yes.
Your number did not
No,
change.
I have not changed that one, but my mobile was changed, so that's why I forgot.
Okay, I will certainly send it. Thank you.
Because I have some work related to that unicyclists, but in sine graph, graceful sine graph. I think the same work can be extended. I just discussed with you.
We'll be happy to talk about it. Thank you.
Yes, thank you, sir.
Thank
If you have any work on sine graphs, please tell me about it so I can put it in my gigantic bibliography of sine graphs, which is at the Dynamic Surveys and Combinatorics next to Gallien's Survey of Graph Labeling.
Yes, sir. I'm going to send definitely my student Jessica Pereira, and my work is already there. Some extended work on sine graph. I'm going to send.
Oh, good.
Excellent. Yeah, so looks like my wish is coming true, sir.
Anyway, I will, Thomas, just we keep on informing you what we are doing in sine graphs.
Very good. And you sent me something yesterday, but I don't have time to look at it yet.
No problem, no problem. Just send for your comments and other things. No.
Okay.
Then is sine
Yes.
graph. Okay.
Very good. Okay. I will let you know.
Because after coming to Christ, I motivated people to work in sine graphs.
Uh-oh.
So there are 2 girls who are at sine graphs. So anyway, I will take care of them. No problem.
Very good. Thank you.
That's what.
I think Father Joseph is a good mathematician. I see he.
Who?
Father Joseph.
Yeah, he's a person of number theory and graph theory.
Oh, okay. That's good for him.
PhD is mixed number theory and graph theory.
Yes, I like his thought.
Algebra also. He works on algebra also.
Oh, no. Well, that's something I can't do.
Yeah, but number theory, and therefore the problem which we are doing, they are mostly from number theory only.
Oh, nice.
The parity sign graph is from number theory.
Right. Okay. Yes.
Rina number was defined by him.
Really?
Yes.
I thought you did that.
So
Oh.
the Rina number's definition came from him. Then I was not able to understand for some time, but now it is very clear to me what is meant by Rina number. Okay.
Yes.
Rina number
Okay,
definition
well, that,
is from him.
I think that's, shall I explain what that is? Do we have time? I think we are beginning.
Yes, we have around 4 minutes to start.
I think the Ernan number of a graph is the number of edges in a smallest cut.
Yes. Yes.
Okay.
Yes.
Yes.
Yes. Yes. Yes.
I don't know if this has been studied. If anyone knows that it has been studied, they should please let us know.
It has not been studied. We have searched a lot of literature. It has not been studied. It came
and it's surprising.
one of the labelings, that is parity labeling.
Well, so people look at maximum cuts, but this is minimum cut.
This is a minimum cut.
And it's completely different, I think.
It's completely different because there are many permutations. There are many ways to label the verses, which may give us a maximum number of negative edges. But we were interested so that we get minimum number of negative edges. Because under that definition, our parity, when we get a sign graph, it is always balanced.
I just thought of something, but I will discuss this more later.
Surely, surely, surely.
We have a talk coming up in 2 minutes.
Yes, so let us welcome the participants and the new person to have the talk continue this conference. Thank you very much, Professor Zaslavsky. Everybody, Professor Paga, Professor Bhutani, Kiran Bhutani, okay? Those who are very far off and they have a different time clock. Okay, thank you very much. Thank you very much. Take care of your health and sleep well.
I'm staying here for a while. I want to see several talks. And thank you, Professor Acharya, for your nice introduction.
Thank you. Thank you. It's a pleasure to see you.
You too. You look so good.
Because I know you will be awake in the night, 1 o'clock, 2 o'clock. Therefore, I have decided not to give the email during that time.
Oh. Oh. Thank you.
Thank you once again, Professor Thomas Zaslavsky and Professor Mukti Acharya.
Thank you.
For our next session, the chairperson is Professor S. Arumugam. Professor S. Arumugam has held the following positions: Professor and Head of the Department of Mathematics at St. John College, Professor and Head of the Department of Mathematics, Mamiyam Sundaranara University, Senior Professor and Dean of Kalasalingam University, Conjoint Professor, School of Electrical Engineering and Computer Science, the University of Newcastle, Australia, Adjunct Professor, Department of Computer Science, Ball State University, Indiana, Visiting Professor, Department of Computer Science, Liverpool Hope University, Liverpool, United Kingdom, Adjunct Professor, BITS Pilani, for a period of 1 year starting from August 2015, which was extended for another year till 2016. He has 50 years of experience in teaching and administration. He has organized 28 conferences and seminars. He has a total of 260 research publications and 23 books published. He has guided 44 candidates for PhD and co-guided 14 candidates. Professor Arumugam's area of specialization includes graph theory and its applications, fuzzy logic and its applications to pattern recognition, topology, geometry, and visual cryptography, social network analysis, and biological networks. He has conferred Lifetime Achievement Award by GATR, Malaysia, during the closing ceremony of the 4th Global Conference on Business and Social Sciences held at Dubai during the year November 2014 to 15 and 16. He has around 6 projects that he has worked on. He is the editor-in-chief of the AKCE International Journal of Graphs and Combinatorics. We welcome you, sir, and I kindly request you to take over.
We start the session now?
Yes.
Are you still time?
No, we can start the session.
Yes, yes.
So I welcome all to the session. The speaker is Dr. Lolita Castellino from Banakal, Karnataka. She is Assistant Associate Professor and Head of the Maths Department at Madhva Vadiraja Institute of Technology. And she had a MSc from Stella Maris College, Chennai, MPhil from Alagappa University, Karaikudi, and PhD from NIT Surathkal. She worked under the guidance of Professor Hegde, and today she will talk about harmonious. And yeah. So I welcome the speaker to present their talk on harmonious colorings.
Hello. Hello.
Yes, we can hear you, Professor Lolita. You can start.
Yes. Good morning, everyone. First of all, I would like to thank the organizers for giving me a chance to present in this conference, ICGLA-2020. Also, I'm always thankful to my guide, Professor S.M. Hegde, for his constant support, guidance, and encouragement. Also, in this occasion, I want to thank my colleague also, Professor Dr. Vasudeva, for his encouragement. I chose the topic harmonious coloring of digraphs. This topic has, I'm closely connected with Professor B.D. Acharya because of this topic, I can say, because this work, this research work we did for the project sponsored by DST. And also, once I got a chance to have a discussion with Professor B.D. Acharya, he had visited our NITK campus, Surathkal, along with Mufti ma'am. And it was a fruitful discussion because I had discussed this topic, harmonious colorings of digraphs, and I came to know the vast knowledge that Professor B.D. Acharya has in graph theory and his keen interest in all the topics. So bowing, seeking his blessings from above, I'm sure he is always blessing the researchers from above. I want to start my presentation. So the outline of the presentation is coloring of a graph, then talk about harmonious coloring of graphs, then harmonious coloring of digraphs, then harmonious colorings of some classes of digraphs, then general results and applications of harmonious colorings of digraphs, and the references. So first, I want to start with coloring of a graph. As you all know, the definition, the coloring of a graph, G is a function that maps pieces of a graph, maybe either vertices, edges, or both, into some set of numbers. Usually it is set of natural numbers or integers or real numbers. They are usually called colors such that the specified property is satisfied. So the reason for using positive integers as colors is that we are interested in the number of colors being used. So there are three types of colorings. That is vertex coloring. The vertex coloring of a graph G is an assignment of colors to the vertices of G, one color to each vertex. So if the adjacent vertices are colored differently, then we say as proper vertex coloring. Then we have region coloring. The planar graph G is said to be K region colorable if each region of G can be assigned one of K given colors so that neighboring or adjacent regions are colored differently. Next, we have edge coloring. The edge coloring of a graph G is an assignment colors to the edges of G, one color to each edge. If adjacent edges are assigned distinct colors, then the edge coloring is a proper edge coloring. So we'll go to our topic, that is harmonious coloring of graphs. So in the year 1983, Hopcroft and Krishnamurthy introduced this topic, the harmonious coloring. So it is an edge coloring. So harmonious coloring of a graph is defined as it is an assignment of colors to the vertices of G, and the color of an edge is defined to be the unordered pair of colors to its end vertices such that all edge colors are distinct. And the harmonious coloring number is the least number of colors in such a coloring, and it is denoted as H of G. So actually harmonious coloring of graphs is an extension of harmonious and graceful labeling of graphs. Hopcroft and Krishnamurthy also showed that the harmonious coloring problem for general graphs is NP-complete, and also the harmonious coloring problem may be viewed as an Eulerian path decomposition in graphs. So it is actually NP-complete problem. Also, he had mentioned in the paper that the harmonious coloring problem is NP-complete even for digraphs. Next, Professor S.M. Hegde and myself, we have extended the concept of harmonious coloring of undirected graphs to digraphs. So speaking about undirected graphs, there are many research work has been done finding the harmonious coloring number for some classes of digraphs or finding the lower bound or upper bound for the graphs. So we, S.M. Hegde and myself, extended this concept to directed graphs. The definition goes like this. Let D be a directed graph with n vertices and m arcs. A function f from V of D to the set 1 to etc. k, where k less than or equal to n, is said to be a harmonious coloring of D if for any two arcs xy and uv of D, the ordered pair f of x, f of y is not equal to f of u, f of v. The pair II is not assigned for any I, 1 less than or equal to I less than or equal to n, then f is called a proper harmonious coloring of D. The minimum k for which D admits a proper harmonious coloring is called the proper harmonious coloring number of D and is denoted as chi h of D. So the difference for graphs and digraphs is in harmonious coloring of graphs, we use unordered pair of colors, and in harmonious coloring of digraphs, we use ordered pair of colors. So this is the example for Peterson graph. Since for unordered pairs, if k colors are using, there are k into k minus 1 by 2 ordered pairs. So altogether, we are using 10 colors for graph, and we are using 5 colors for digraph, Peterson digraph. So here, orientation we have taken in general, and there are k into k minus 1, that is 5 into, actually 5 into 4, 20 ordered pairs, but we could take only 15 ordered pairs here because 15 edges are there. So next, since the harmonious coloring problem is NP complete, either we can find the exact harmonious coloring number for some classes of digraphs, or we can, if it is hard to find, then we can compute some upper or lower bounds. So here we found the lower bound for the harmonious coloring number. The common bound is that delta plus 1, where delta is the maximum in degree or out degree. The harmonious coloring number lies between maximum in degree or out degree of the vertex plus 1, or it lies between maximum, it can have n. The number of harmonious coloring number can be n. So this is the lower bound that we found. For any digraph D, the harmonious coloring number is greater than or equal to ceiling value of 1 plus square root of 4m plus 1 by 2, where m is the number of arcs of D. So this is easy to find because k into k minus 1 ordered pairs are there, and we have the number of arcs, that is m, should be always less than or equal to k into k minus 1. So using that, we will get this result. Then we found the harmonious coloring number of some classes of digraphs. For the clarification, I have given the definitions also for different classes of graphs, since we are giving the orientation. So an oriented path is called unipath if in degree of V is equal to out degree of V is equal to 1 for every vertex V except the first and last vertex of the directed path. So we found the harmonious coloring number of the path Pn, unipath Pn is the ceiling value of 1 plus square root of 1 plus 4 into n minus 1 by 2. So we are comparing this with the lower bound that already we found. Here m number of arcs is equal to n minus 1. And this is the example of unipath P7. So here 6 ordered pairs are there. All the ordered 6 ordered pairs have been used. 1, 2, then you have 1, 3, then 2, 1, then 2, 3, then 3, 1, and 3, 2. See, all the ordered pairs have been used. Next, we found for directed star. Directed graph in which the underlying graph is a star is known as a directed star. So the harmonious coloring number of directed star is maximum of in degree of V or out degree of V plus 1, where Sn is the directed star with n vertices and V as the central vertex. So we have considered all the orientations of S5. So in the first case, the maximum out degree is 4 here. So the harmonious coloring number is 4 plus 1, 5. That's why we have 5 colors have been used. And in the second case or third case, the in degree is equal to the out degree of V. So here in degree out degree is equal to 2. So 2 plus 1. So 3 colors have been used. Next, we found for unicycle. So a directed cycle is called unicycle if in degree of V is equal to out degree of V is equal to 1 for any vertex V of the directed cycle. So the harmonious coloring number of Cn or unicycle is k plus 1 for n is equal to k into k minus 1 minus 1 and k for n is equal to k minus 1 into k minus 2 plus 1 etc. K into k minus 1 minus 2 comma k into k minus 1 where k is nothing but the ceiling value of 1 plus square root of 4n plus 1 divided by 2. So here for n values for the n k into k minus 1 minus 1, it's not possible to find with the k because one ordered pair will be repeating. That's why we have to consider k plus 1 colors. So this is the example for unicycle C12 where we are using 4 colors. So all the 12 ordered pairs have been used here. Next, unicyclic wheel. You know the definition of directed wheel. Directed wheel with n vertices is a digraph obtained from the directed cycle C n minus 1 and k1 by joining every vertex of C n minus 1 to the vertex of k1, where the directed cycle C n minus 1 is called the ring and the arcs joining k1 are called the spokes. The vertex of k1 is called the central vertex. If the ring of a directed wheel is unicycle, then the wheel is called unicycle. So we have taken the spokes as different orientations and we have taken the direction of a ring as unicycle. That's why it is called unicyclic wheel. And this is the theorem where the harmonious coloring number, there exist 3 cases here. For wheel, it is equal to in degree of V plus out degree of V plus 1, where V is the central vertex. And for n is equal to 5 and 6, it is n if in degree of V is equal to 0 or out degree of V is equal to 0. Or it is equal to in degree of V plus out degree of V. And third case for n greater than or equal to 7, harmonious coloring number of Wn is maximum of in degree of V, out degree of V plus 1. So this is the example for W7 with various orientations. So if you can check here. So in the first case, the in degree, it has maximum in degree. So it is 6. So there are 6 plus 1, 7 colors have been used, so etc. We can check. Next, we considered the tree, NRA tree. An out tree is a rooted tree with its edges oriented from the root. So we have taken the orientation from the root to the leaf and we defined it as out tree. And the harmonious coloring number of any n array out tree is always less than or equal to n power floor value of L by 2 plus 1 minus 1 divided by n minus 1, where L is the level of the tree. And we consider here the level from 1 to 3, etc. And this is the example for trinary out tree T3, and we are using altogether 13 colors here. The minimum colors can be used is 13. Next, we extended this results to regular digraphs too. Now, the definition of regular digraph is a digraph D is R regular if the in degree AD of V is equal to out degree OD of V, that is equal to R for every vertex V of D. So we find another lower bound for harmonious coloring number where D is a regular digraph and this is the lower bound, that is harmonious. If D is a R regular digraph, then harmonious coloring number of D is always greater than or equal to ceiling value of 1 plus square root of 1 plus 4 Rn divided by 2. And we have found for two regular digraphs, that is torus and circulant digraph. This is the definition of torus. An n-dimensional torus is defined as an interconnection structure that has k0 cross k1 cross etc. kn minus 1 nodes, where ki is the number of nodes in the ith dimension. Each node in the torus is identified by an n coordinate vector x0, x1, etc. xn minus 1, where 0 less than or equal to xi less than or equal to ki minus 1. Two nodes x0, x1, etc. xn minus 1 and y0, y1, etc. yn minus 1 are connected if and only if there exists an I such that xi is equal to yi plus or minus 1 mod ki and xj is equal to yj for all j not equal to I. And for this torus, we define the orientation O of t as the horizontal cycle are unidirected in the clockwise sense and the vertical cycles are unidirected in the clockwise sense. So this is the orientation we gave for, this is one example for 4 cross 4 torus. So these are all horizontal cycles and these are all vertical cycles and all are in a clockwise direction. So this is the, we found the result for n cross n torus. The harmonious coloring number of n cross n oriented torus O of t is k plus 1, where k is equal to ceiling value of 1 plus square root of 1 plus 8n square by 2. And this is the example for 3 cross 3 torus. And we are taking the harmonious coloring number is 6 here. Next, the circulant digraph. The definition is given by Espas and Turner. A circulant digraph denoted by Gn of S, where S is a subset of 1 to etc. n minus 1 n greater than or equal to 2, is defined as a digraph consisting of the vertex set V is equal to 0, 1, etc. n minus 1 and the arc set E that is equal to the ordered pair ij. Then there is S belonging to S such that j minus I is congruent to S mod n. And this is the example of G8 of 1, 3. We are considering here small s as 3. So we found the result for Gn of 1, 2, the circulant digraph. So the harmonious coloring number of circulant digraph Gn of 1, 2 lies between k and k plus 1, where k is equal to ceiling value of 1 plus square root of 1 plus 8n by 2. And this is the example for circular digraph Gn of 1, 2. The harmonious coloring number is 6 here. Also, after we found, we extended the problem of harmonious coloring number of graphs to digraphs, Professor Keith Edwards have got some few results in this harmonious coloring number of digraphs. So he found few results is G be a directed graph with m edges and maximum degree delta. He found some upper bounds. Then h of g is always less than or equal to 2 square root of delta m plus half delta into delta plus 2 into delta square plus 1 plus 1. And also for an oriented tree, he found an upper bound as harmonious coloring number of g is always less than or equal to 2 square root of m plus half delta into delta square plus 2 delta plus 3 plus 1. Also in the paper, he proved that the problem of directed harmonious chromatic number is NP complete even for directed graphs with maximum in degree and out degree at most 2. So these are the results as far as I know are there for harmonious coloring of digraph. Much work has not done in this harmonious colorings of digraphs. So the applications of harmonious colorings of digraphs is, it is used in communication networks, for example, transportation networks or computer networks. Then it is used in radio navigation system. Also, it is used in data compression, a design of minimal hash function. As Hofcroft and Krishnamurti, he has written in the paper that the harmonious coloring problem is closely related to constructing minimal perfect hash functions. So this is one of the applications in data compression. Then it is also used in clustering. So these are the references. This is the first paper by Hofcroft and Krishnamurti on the harmonious coloring of graphs. So these are the papers in digraphs, myself and Professor S.M. Pigre and myself. Then you can find the bibliography of harmonious colorings and achromatic number in this. Main literature can be found in this because almost all the papers are there in this bibliography. Thank you.
Any questions?
Stephanie?
I'm here.
Yes, Sanford, yeah. Just check if there are any questions on YouTube.
From the participants, there are no questions. If there are any questions from the panel list, then we can go ahead with that.
Okay. You should give some good lower bounds for the harmonious chromatic number, okay? You have given lower bounds.
Yes, sir.
Because lower bound is more interesting for coloring parameters because less than or equal to can easily prove. The chromatic number is greater than or equal to is really difficult in general, right?
Yes.
Now, is there any digraph where the lower bound is attained in your case? Digraphs which are reaching the lower bound in information.
Below the lower bound, sir? No, sir, we have not yet got the results in that.
Because otherwise we don't know whether the bound is tight or not.
Yes, sir. Felt it is tight because we are considering that
some classes of graphs which actually attain the bound would be very interesting.
Yes.
Yeah.
Yes, sir.
I think unidirectional directed path is attaining the bound.
It is attaining the bound, yes, it is equal.
What about unicycle? We have
no, unicycle is not attaining.
Unidirected cycle.
The 8th slide gives the bound.
Only one unicycle.
For unicycle, sir, only for n equal to k into k minus 1, it is not attaining. The rest of the cases, it is
attaining that.
It is attaining.
What about the this one, complete bipartite graph? If you take unidirectional, any
The
direction.
complete bipartite graph, we have not checked, sir, because we have to give the directions for that.
Okay.
Anyway, I will try checking that, sir.
So till now, there is no upper bound known so far for direction.
Upper bounds, sir, few upper bounds have been found by Professor Keith Edwards.
Okay. Okay.
These are the upper bounds.
Okay. In terms of maximum.
Only two for digraphs, sir.
Okay.
Not much work has been done in this harmonious coloring of digraphs.
Okay.
I'd like to ask a question about the two torus. You had formulas for the two torus. I think I missed those.
This is the
formula.
torus. Formula? Yes.
So this is the two-dimensional torus.
Yes. No,
Okay.
this is...
The formula is for the two-dimensional torus. This is the definition of the n-dimensional torus.
Yes, sir. This is the definition of n-dimensional torus. We have taken n as 1, sir.
Okay, I understand this.
Yes.
You have a formula for the number, what's it called? Harmonious coloring number?
So harmonious coloring for torus is k plus 1, where k is ceiling value of 1 plus square root of 1 plus 8n square by 2.
Well, that's undirected. How about directed?
Directed. O of t. We have defined the directions, sir. We have given vertical cycles and horizontal cycles as unicycles.
Okay, so they are directed. Okay,
Yes.
By the way, this graph is known as the toroidal grid graph.
Yes, grid graph, yes.
It's a toroidal grid graph.
Yes.
So in case you probably knew that. Okay, so when you calculate your harmonious coloring number, is it for this orientation or is it for no orientation? I'm not clear
for
about
this
that.
orientation, for this particular orientation.
This is like a cyclic orientation, in a sense. Everything is a cycle.
Yes, sir. Cycle and unicycle.
A unicycle, yes. Can I see the next slide, please, with the formula?
Is it sound diagram?
Pardon, ma'am, I didn't.
Oh, thank you. So why is it a square root? It reminds me of the formula for the chromatic number of a surface.
I didn't get, sir.
There's a formula for the chromatic number of a surface. So there's the largest chromatic number of a graph that can be drawn in the surface. And it looks a lot like this, although it's not the same. Has a square root.
So we have considered here because the lower bound for regular digraphs.
His question is why there is a square root in your calculation. He's telling this formula looks like the chromatic number for the surface.
Okay. Sir, square root is there because we are having k into k minus 1 ordered pair, sir. So we are taking the bound as always the number of arcs is must be less than or equal to k into k minus 1. So when we calculate that value, k value, we will get square root, sir.
So it's natural to have a square root. Okay, that's,
yes, sir. Yes,
good.
Sir.
What about an n sub 1 by n sub 2 torus? Can you do that?
I didn't try, sir.
That instead of n times n, it's n sub 1 times n sub 2.
Okay.
Is that much harder?
I have not tried, sir. I can see.
Okay, well, thank you. I was wondering how that would look. Would you have n1 times n2 instead of n squared? That would be interesting. It's the number of vertices.
Yes, sir. I will try that, sir. I have not tried yet. Thought n cross n would be better. I think it is an open problem. We can try it.
I think so. Thank you.
Yes, yes. Thank you, sir.
Can I ask one question?
Yes, ma'am.
For the graphs, you have harmonious labeling, is it?
Yes.
So my question is that suppose I have a graph, I give it harmonious coloring, okay? So after giving the harmonious coloring, I orientate. I make the orientations of that graph from low to high. That is, they are the numbers, no? Basically they are labelings, okay? So
Yes.
I make the direction of the edge from low to high. If I have adjacent vertex with label 1 and 5, my orientation will be from 1 to 5. So for the whole graph, I get a diagram for the
Yes,
graph,
ma'am.
which is
Yes.
which you have given harmonious labeling, and then I get a diagram where the directions are from low to high. So when that means in your case we get many diagrams depending upon the orientation of this one. But here my orientation depends upon the harmonious labeling of the graph. And digraph we are obtaining from low to high. The directions are from low to high. So what my question is, once you have a harmonious coloring for a graph, you have its maximum number of colors. And when you do it from low to high, what is the effect? No, what will be its number? How many colors you will be requiring?
Ma'am, I think we cannot take from low to high because we are considering here ordered pairs. So when we consider 1, 5, we have to consider 5, 1 also. Otherwise, it will not be minimum. The definition of harmonious coloring number not come. That's what I feel.
And that means you means from the graph, when you come to digraphs, you will always have a cycle of length too. If 1, 5 is there, 5, 1 should be there. That's what you are telling.
It need not be there, ma'am. But for few cases, it will be there.
Color to some other edge. Because
Let me ask, may I ask something? It sounds like she's saying that the digraph harmonious coloring number is always less than the graph harmonious coloring number.
Yes.
So you can always do better when you orient the edges the way you suggested, Professor Acharya.
Okay, I don't know. Because I
Is
don't
it true? No,
I
can you always do better? Is that a fact?
I think so because I have not seen in that direction, sir. But I feel usually the harmonious coloring number of digraph is less compared to harmonious coloring of graph. Because there we are using K, suppose K colors are used because
how much
K.
You can reduce? How much you can reduce?
That we have to check because there we are using ordered pairs K into K minus 1 by 2 for graphs, and for digraphs we have K into K minus 1 ordered pairs. So the bound lies between that.
So is it always true that you can reduce it by at least 1/4? You can't reduce it by more than half, but can you reduce it always by a certain proportion?
Yes, I feel we can reduce.
And what is that proportion, like reducing by 1/4 or 1/5 or 1/3 or 1/pi?
I have not checked in that, sir. Anyway, I will.
No. No,
because it
these are
depends. I
research
feel.
questions.
Yes.
These
No,
are,
it's
because
these are research questions.
There
Good.
may be some directions to the orientation to the edges where you cannot go less than that number of colors.
Mm-hmm.
That is minimizing the number of colors in your harmonious digraphs.
Yes. That we'll find out, sir. Anyway, it is really an interesting question. I think we have to see in that direction. I have not seen in that direction yet, sir.
Sure, there's a lot of work. Okay, no
yes,
problem.
yes, ma'am. Lot of work is there because this is just the starting part.
And because the platform is open only for proceed, go ahead. Okay, not
Yes,
stuck there. Go ahead, not stuck there.
Yes, ma'am. Yes, ma'am.
Okay, nice.
Thank you, ma'am. Thank you so much.
Are there any other questions from the panel list? Okay, so this means that we have come to end of the session. I thank Professor Lolita Castellino for this session, and I also thank Professor Arumugam for chairing this session. Thank you so much. Professor Jessica, can we move ahead with the next session?
No, I think we'll wait. Maybe you can give some announcements to the participants on YouTube, as in the feedback link. Okay, maybe I'll go ahead of that. So this is instruction to the participants. We will post the feedback link only on the YouTube chat box. Like yesterday, it will not be shared on WhatsApp groups. So all of you have to keep a track. We will also be announcing the same. So when we are going to post the attendance links on the YouTube chat, we are going to announce it also. So please keep a track. It will be open only for half an hour to 45 minutes. So you have to give your attendance within that much time. And we will not entertain any requests to give you the feedback link personally. So please keep a track of the attendance link on the YouTube chat only. I repeat, it will not be sent or posted on WhatsApp groups. Yesterday, there was a technical issue, and because of that, we had to post it on WhatsApp groups and the Telegram. Today, I repeat, we will not be sending it on WhatsApp group and the Telegram groups. So please keep a track and keep attending the sessions. That's important. You will be given certificates based on your attendance for today and tomorrow.
What about yesterday?
Yesterday, ma'am, there was some issue, so probably they have to have attendance for at least 2 sessions out of at least 2 days out of the 3 days.
Okay.
So yeah. So we have some more time. We start the next session at 12. So probably we can. Yes, 10 minutes are there, or we will start at 11:55. We can start.
Whose talk is there?
If the next speaker is ready,
yes.
If the chairman is ready, we can start.
Okay.
So that we can go for lunch little early.
Yes.
And have a good lunch, hot lunch.
Yeah.
Yes. So is Professor Shivraj Kumar
Yes,
present?
yeah.
Okay, yeah, that's good. That's great. And Professor A.K. Handa, are you there?
I'm here.
Yes. Okay. Yeah.
Shall I share the screen now?
Yes, you can. So Sanford, you can go with the introduction. Go ahead.
Yes.
Thank you.
The chairperson for the next session is Professor Adarsh K. Handa. He attained his master's degree in mathematics from Goa University in the year 1997. He then pursued his MPhil in mathematics in commutative rings from MK University under the guidance of D.A. Mahapatra, Goa University. He is currently an associate professor at Path Kosisang College of Engineering, Vedna, Goa. He is currently pursuing his PhD to BITS Pilani, Goa, under the guidance of Dr. Tarkeshwar Singh. His research interests include graph labeling and algebraic topology. We welcome you, sir, and request you to kindly take over.
Thank you very much. It's my pleasure to introduce speaker Dr. Shiva Kumar. He has done his master's degree from University of Mysore, PhD from NIT Surthkal, and his research interests are combinatorics and number theory. He has a 10 years teaching experience. Presently, he is associate professor in National Institute of Engineering, Mysuru. Professor, I welcome you to start your talk.
Thank you, sir.
Thank you. Welcome. Yeah.
Am I audible? Hello?
Yes.
Yeah, is the screen visible?
Yes. Visible.
Yes, it is.
Yeah, thank you so much. Good morning to all of you. So I would like to thank organizers of this conference for giving me an opportunity to discuss one of the very interesting problem in the theory of graph labeling called graceful labeling of digraphs. In this talk, I mainly focus on discussing some of very interesting results. I mean the proof of 3 conjectures in the theory of graceful digraphs.
which we have done when I was at NITK Surathkal and associated with Professor S.M. Midday. So I hope participants are familiar with what is graph labeling and its applications, and also participants are familiar with what is graceful labeling of a digraph and its characterizations due to Bloom and Su. With this introduction, but for the sake of completeness, let me quickly define what is a graceful labeling for a given graph, undirected graph. Suppose G is a graph with Q number of edges. Now G is said to be graceful if we assign to each vertex a distinct number from the set 0 to Q, such that the label on the edges is defined by the absolute difference of the labels on the end vertices. If the edge labels are all distinct and it belongs to 1 to Q, then G is said to be graceful. And this was defined by Alexander Rosa in 1966. And then this idea of graceful labeling for undirected graph has been extended to directed graph by Bloom and Su in the year 1982. And here we use, instead of 0 to Q, here we are using the elements from the set ZQ plus 1. Suppose D is a directed graph with Q number of edges. Now we are not using the element just from the set 0 to Q. Instead, we are using the elements from the set ZQ plus 1, and it is a finite cyclic group. So very rich in structure. And here the edge label, it is an ordered pair U comma V. Therefore, U comma V ordered pair denotes the U is directed to V. In that case, the edge label is defined as G of...
Excuse me. Hello?
Yes, sir.
Yeah, why it can be a set, any set containing 0 to Q, no? Why you have to take Z Q plus 1? It is not necessary.
But sir, the operation, while we define the edge label, we use modulo Q plus 1.
Yeah.
So that brings ZQ plus 1 into picture.
Fine.
Yeah, since the edge label is defined as G of V comma G of V minus G of U into mod Q plus 1. So it's so natural. We have to plug in ZQ plus 1 into picture. Is it fine, sir?
Fine. Go ahead.
Yes, sir. If the ARP labels are all distinct, then we say that it is graceful. Let me quickly go through an example. Consider the unidirectional cycle C6. Here we have 6 vertices and 6 edges. Therefore, we have to use the elements from Z7 to label the vertices. Here 0, 6, 1, 4, 2, 3. These are all the elements of Z7 and they are all distinct. And according to the definition, the label on the first head, that is 6 minus 0. Here the head 6 minus 0 modulo 7 is 6. Then 1 minus 6 modulo 7 is 2. And 4 minus 1 is 3. And 2 minus 4 is minus 2. Under modulo 7 it is 5. And 3 minus 2 it is 1. And 0 minus 3 is minus 3. Minus 3 modulo 7 is 4. And we can see that the edge labels are all distinct. Therefore, this is a graceful labeling. This is one of the graceful labeling for C6. And these are the characterization. As I said, I will skip all these details. One is sequentiability and the other one is the complete mapping. These two are the characterizations made by Bloom and Su in his introductory article. I will skip all these details. Now let us move on to the main results of this talk. So Bloom and Su in the year 1985, they mentioned that for n less than equal to 11, all unicyclic wheels are known to be graceful, except for n equal to 6 and 10. And they also have made conjecture that all unicyclic wheels are graceful. We can see that, and here Bloom and Su, they have used quadratic residues to label the vertices of the wheel. And even with that, they are unable to find the graceful labeling for n equal to 6 and 10. And then in 1994, Du and Son conjectured that the digraph n.cm. Here there are n copies of cycle cm with one common vertex is graceful. And also in 2008, Zhao Lingiki et al. Conjectured that for any even n and m greater than equal to 14, the digraph n minus cm is graceful. Now, before move on to the defining the structure of these directed graphs and its gracefulness, let me spend some time shall I continue?
Yeah.
Yes, sir. Before move on to discuss about the structure of this diagram, let me spend some time in discussing what is our first impression on finding the graceful labeling for a given directed graph. For that, let me consider this unidirectional cycle Cn. Here there are n edges, therefore one has to use Zn plus 1 to label the vertices. So assume that A1, A2, A3, A4, etc., An, these are all the elements from the set Zn plus 1, and B1, B2, B3, etc., Bn, these are all the non-identity or non-zero elements of Zn plus 1. Now, suppose if it is graceful, then all these entries, AIs and BIs should be distinct. Now, in order to say that it is graceful, then A2 minus A1 should be congruent to B1 modulo n plus 1. Similarly, A3 minus A2 should be congruent to B2 modulo n plus 1. Similarly, A4 minus A3 should be congruent to B3 modulo n plus 1, etc. A1 minus An should be congruent to Bn modulo n plus 1. Essentially, we end up with the system of simultaneous congruences. This will be governed by the graceful labeling of directed graph of unicycle Cn. Now, if we look at these expressions, these simultaneous congruences, if we look at the left-hand side, if we add them, we end up with 0, basically congruent to 0. So A2, A2 get cancels, A3, A3 get cancels, A4 get cancels, etc. At the end, this A1 and this minus A1 get cancels, and we end up with 0. Now, from the linear algebra, immediately we can say that if this system of congruences has a solution, only if the right-hand side, B1 plus B2, sum of BIs, I mean B1 plus B2 plus B3, etc., Bn, should also be congruent to 0 modulo n plus 1. And so this is one of the necessary condition to be, this digraph to be graceful. And also, we can see that here this n and this BIs, sum of BIs is congruent to 0 if and only if n is even. If n is odd, then it is not equal to 0. This is not congruent to 0 modulo n plus 1 because the middle element will not have additive inverse, therefore it will not become 0. We end up with the sum end up with n by 2, something of that kind. So if n is even, then the sum will be 0. Therefore, from this immediately we can say that this digraph is graceful only if the number of edges is even. If the number of edges is odd, then it is not graceful. We can quickly say that from this simultaneous congruences. But now this condition is not sufficient. It is just a necessary condition. Now, in order to say that this digraph is graceful, if and only if we consider this first two expressions, here A2 and A2 get cancels, and we end up with A3 minus A1 equal to B1 plus B2. And here, since it is if it is graceful, then A3 and A1 should be distinct. Therefore, it is not 0. Therefore, B1 plus B2 also should not be congruent to 0 modulo n plus 1. Similarly, if you consider first 3, first 4, whatever, in general, if you consider any path here in this directed graph, any path which is not a cycle, then the sum of the labels on the edges should not be congruent to 0 modulo n plus 1. That will be the sufficient condition to say that whether the given digraph is graceful or not. So from this, what we can figure out is that, what I mean to say here is that we normally in the definition of graceful labeling, we used to label the vertices first and then we define the edge labels. But here from this system of simultaneous congruences, we no need to go for labeling the vertices. if we are able to label the edges according to the system of according to the demand of the simultaneous congruences, then vertex labels are automatic. Suppose if I am able to arrange the elements of Zn plus 1 minus 0 in such a way that if you consider any subset consecutive numbers, not subset, consecutive numbers, if it is not 0 modulo n plus 1, then vertex labels are automatic. We no need to find them. So that itself gives us the graceful labeling. Maybe while solving or while discussing the proof of wheel conjecture, we will discuss that. So from this, we can immediately figure out that if the digraph D is balanced, I mean the in degree and out degree of each vertex is same, then the left hand side of the simultaneous congruence is always 0, right? Therefore, if the digraph D is, balanced digraph is graceful, then the number of arcs in the digraph should be even. If it is odd, then it is not graceful. But here we don't know the other way around. I mean, if you, for a given balanced digraph with even number of edges, if you can ask me whether it is graceful or not, I don't know. Still, till today, we don't know. Whether can you find a digraph with even number of balanced digraph with even number of edges where it is not graceful? We don't even have an example. Okay, so now with this, let me move on to discuss about the proof of the unicyclic wheel. All unicyclic wheels are graceful. Now, before move on to the proof, let me define the structure of this directed graph. So the directed wheel is said to be outspoken if all spokes point out from the hub to the rim. I mean, all edges from the central vertex to the rim, if it is pointing towards the rim. And we say that it is inspoken if all edges point from the rim towards the central vertex hub. And if the rim of the directed wheel is unicycle, then we say that wheel is called unicyclic. So let me give a diagram. Yeah, this is what I was telling about. This is an example of outspoken unicyclic wheel W6. Here, this is hub, central vertex, and this is rim. And here, these are all called spokes, and it is pointing towards the rim. Therefore, it is outspoken. If these edges are pointing towards the hub, then we say that it is inspoken. Once we prove that the outspoken unicyclic wheel is graceful, then inspoken unicyclic wheel is also graceful. It is quite natural. We will see that. So now this is the corresponding system of simultaneous congruences governed by, suppose assume that this directed wheel, outspoken unicyclic wheel is graceful, assume that, then A0, A1, A2, A3, etc., A6, these are all the elements from Z13 because there are 12 edges, there are 6 spokes and there are 6 edges on the rim. And B7, B8, etc., B12, these are all the elements from Z13, non-identity elements. So now if we consider the second half of this system of equations, here the unicycle, if you consider, we have already seen that the sum of the labels on the edges of this rim must be add up to 0, right? Why? Because if you look at the system of congruences, A2 get cancels, etc., and this A1 and this A1 get cancels, therefore this will be 0. This adds up to 0. Therefore, B7 plus B8 plus B12, I mean the labels on the rim should be congruent to 0 modulo 13, right? And now 13 is an odd number. Therefore, the total sum B1 to B12, 1 to sum of 1 plus 2 plus etc. 12 is congruent to 0 mod 13. Therefore, this insists that the sum of the labels on the spokes is also congruent to 0. So this is what I have mentioned in this proposition. If an outspoken unicyclic wheel is graceful, then some of the labels of the spokes should be congruent to 0 modulo n plus 1. Therefore, if we want to find the graceful labeling for a outspoken or inspoken unicyclic wheel, then one has to partition the set. Suppose if for a general n, Wn, it has 2n edges, then we have to go for z set to z2n plus 1. Then the sum of the labels on the edges of the spokes should be congruent to 0, and some of the labels on the rim also should add up to 0. I mean, one has to partition Z2n plus 1 into Z2n plus 1 minus 0 into two subsets, two disjoint subsets, so that, and with equal number of elements, that is n. So both of them should add up to 0. That is the necessary condition for the unicyclic wheel to be graceful. But now this is not sufficient. Now we can easily figure out that the sufficient condition for this wheel to be graceful is the following. So here if you look at the spokes, so this A2 minus A1, here you consider the first two congruences, and now I subtract this expression from the second expression, then we end up with A2 minus A1, because A0 and A0 get cancels if we subtract them. Then we end up with B2 minus B1. But here A2 minus A1 is B7, therefore B2 minus B1 should be equal to B7. So I mean B2 minus B1 should be equal to B7. And similarly, if we go to the third expression, and if we simplify them, we end up with B3 minus B2 should be equal to B8. And similarly, B4 minus B3 should be equal to B9. And similarly, B5 minus B4 should be equal to B10. And similarly, B6 minus B5 should be equal to B11. And at the end, B1 minus B6 should be equal to B12. I mean, if we are able to partition the set in such a way that, it satisfies these conditions, then W1 is graceful and the vertex labels are automatic. We no need to find them. We can start assigning the central vertex to be 0, and we can, according to the B1, we can keep label the vertices. Right now, let me show the graceful labeling of W6. So this we have found using the same idea. So here we can see that 5 minus 1 should be equal to 4. Then under modulo 13, then 3 minus 5 is minus 2. So it is congruent to 11 modulo 13. Then 10 minus 3 equal to 7. And 12 minus 10 equal to 2. 8 minus 12 is minus 4. Minus 4 is congruent to 9 modulo 13. And 1 minus 8 is minus 7. Minus 7 is congruent to 6 modulo 13. And here we can start with 0. You can start with any number from the set Z13, but let us, for the sake of simplicity, let us start with the vertex label 0. Now the head label is 1, therefore if you put 1 here, then 1 minus 0 is 1. And now, 5 minus 0, since the central vertex is 0, we can keep the same head labels on the vertices. That works out, right? So this is the graceful labeling for W6. And similarly, by using the same idea, we can find the graceful labeling for W10 as well. Now let me move on to discuss the proof of this conjecture for general n. So the idea here is we partition, we divided the proof of this conjecture into 4 parts, which depends on n. If n is one case is, the first case is n congruent to 0 modulo 4. And the second one is n congruent to 2, then n congruent to 3, and n congruent to 3 modulo 4, right? Let me discuss, this, when n is congruent to 0 modulo 4, then this is the head labels. So here, let me go back to this. Here we can see that if we are able to partition the set of integers in such a way that some of the labels on the spokes should be 0 and some of the labels on the rim should be 0. So one idea could be, suppose if n is even, the number of spokes or number of edges on the rim is 0, even, then life is very simple. Because since it is even, what we can do is we can consider n by 2 entries, n by 2 numbers from the set, Z2n plus 1, and its additive inverses, corresponding additive inverses. Then if you add them, it will be 0. So immediately one can choose, that pattern to label the wheel Wn, right? So that is what I am using here. Every alternative vertices I choose, odd numbers, 1, 3, 5, etc., and the corresponding additive inverses I will keep tracking from the right hand side. I will end up with the graceful labeling for Wn. Maybe this is the example. Here we can here W12 where n is congruent to 0 modulo 4. Here what I mean to say is that, suppose, yeah, you can see, you divide this into two parts. One is 1, 3, 5, 7, and I will come back 9 and 11. And here in the second half, I will start with 14, then 14, then 20, then 18, then 16, and then 22 and 24. So I use this pattern to label the edges of the W1 if n is congruent to 0 modulo 4. And since we keep 0 to be the central vertex, label of the central vertex, the vertex labels are automatic. So it takes the same label of the spokes. So this gives us the graceful labeling, and if we transform that into vertex labels, yeah, this is the algorithm to define the graceful labeling for the given vertices. And similarly, this is for n congruent to 2 modulo 4. Yeah, again we consider the numbers with additive inverses, and we aligned in a different way to get the graceful labeling. And this is for n congruent to 1 modulo 4, and this is for n congruent to 3 modulo 4. Okay, so this proves the graceful labeling for the outspoken wheel to be graceful. Now let us move on to the next conjecture. So I choose, the digraph n minus cm. So let me define the structure of this directed graph. N minus cm denotes the digraph which is obtained from the n copies of cycle cm with one common edge. Let me take the example. So this is here, we have 3 copies of cycle with one common edge, and each cycle with this common edge, each cycle will have 7 edges. This is C7. Basically, we have 3 copies of C7 with one common edge, right? So this is the structure of the digraph. Here also, if we, so before move on to the proof of this conjecture, let me give some of the results which is done before proving this conjecture. So Xirang and Jirumutu have attempted to prove this conjecture for m equal to 15, and then for m equal to 17, Zhao et al. Proved this. And then in 2012, we have settled this conjecture completely. Again, we can go for using system of simultaneous congruences. And before that, so if you look at this, digraph, suppose, if I label this as A1, this as A2, A3, etc. In general, for M, Cm, it is Am, right? And similarly, I will label the vertex this as Am plus 1, this as Am plus 2, Am plus 3, etc. A to M. So, and so on. I will label the vertices in this way. If I do that, I will end up with the system of simultaneous congruences. And here, before move on to, so by looking at the previous results, we can prove this conjecture in the following step. One is the sum of the labels on the edges of this unicycle, first unicycle with this common arc should be congruent to 0. Modulo, here we have how many edges? 6, 7, 6, 13, 13 plus 6, 19. So we have to label the edges so that the sum of the labels on the edges with this common arc should be congruent to 0 modulo 20. Similarly here, the sum of the labels on the edges of this path with this common edge, and then we get a cycle, that also should be congruent to 0. Similarly here, the sum of the label on the edges of this path with this cycle should also be congruent to 0 modulo 20, right? Therefore, before that, one has to choose the label on this edge, right? If we solve the system of simultaneous congruences, we end up with the label on this common edge. That I will show it right now. Yeah, this is the system of simultaneous congruences for general n minus cm. And here I'm giving proof for the case where m is even, therefore I use 2m without loss of generality. For m odd, the proof is quite different. I will skip the details. Okay, so here if we solve the system of simultaneous congruences governed by n minus cm where n is even, we end up with this system of this congruence. After solving it, the total number of edges is 2m minus 1 into n plus 1. And now if we simplify this further, we end up with this. So So A1 minus A2M, the label on the edge, will be fixed now. If we solve this, we end up with this label on the common arc, right? But now here the total sum, this we are using the labels from the set Z2M minus 1 into N plus 2, right? Minus 0, because in the edge label 0 is not allowed. And if we, the total sum, 2M minus 1 into N plus 1 into 2M minus 1 into N plus 2 should be equal to this common label plus this. Here N denotes there are N copies, right? There are N copies of cycle, and now each cycle will receive, some of the edge label will be this. I will fix this with this 4mn into m minus 1 plus 4m plus n minus 2 divided by 2 plus 2m minus 1 into n plus 2 by 2 should be congruent to 0. So there are n copies. This n denotes the n copies of cycles, right? So once it is fixed, I will prove in the following lemma. So here this lemma says that I'm basically partitioning this set yes. I'm using the different name here yes because here P is deleted. P is not a part of the set because P is the label on the common edge. It is taken out because it is already fixed. We are not going to change it. It is 2m minus 1 into n plus 2 divided by 2. Now we partition this set yes into n disjoint subsets, right? And each subset will have 2m minus 1 number of elements, so that the sum of each subset is equal to this. And we are going to prove this using generating function. Initially what we do is we keep all the elements of this set yes in this matrix, where P is not missing in this matrix because P is not a part of this set. And so I will just put the first n elements in the first column, second n elements in the second column, etc. And now what we do is we use generating function to find such that x1, I will take it x1 from the first column, I will take x2 from the second column, etc. I will take x2m minus 1 from the last column. I will choose one element from each column so that it should add up to 4mn into m minus 1 plus 4m plus n minus 2 divided by 2. I mean, basically I am trying to prove that the sum of the labels on each path, with each cycle with common edge should be add up to this, right? For that I am using generating function. So this is the generating function. I will skip the details, it is laborious, so I will skip all the details. And basically here what we do is I will find the solution for each element of this matrix. Say for example I will fix 1, and I will find in this I will choose x1 to be 1, and I will allow x2, x3, etc., x2 minus 1 to be the elements from these columns, and it add up to this number. I will find what is the number of solutions by using generating function, and I will denote it by the number of solutions including 1. I denote it by n11, capital N11, right? Similarly, I fix 2 as x1, and I allow the entries from rest of the columns, x2 from second column, x3 from third column, etc., and add up to this number, and I will denote it by n21. Similarly, I will denote the number of solutions of this number by n31, etc. I keep doing this for every entry of this matrix. And what we prove here is that this ni1, the number of solution ni1 is if you fix the row, the first column, then ni1 is positive. The number of solutions of each entry in the first column is positive, right? And we can also prove that the number of solutions of the first column is the same as the number of solutions of each entry in the other columns except j equal to m. Why? Because in this matrix P is missing, therefore this column is totally different from all other columns. Therefore the number of solutions is positive for all entries of the matrix except that column. Similarly, we can prove that even by considering that column, and we can prove that it is positive. NIM is positive for every m, even for j equal to m, it is positive. Fine. Now, I will consider the minimum of all these solutions. The moment I consider the minimum of all these solutions, then I end up with the number of solutions for this directed graph, right? Now this says that the S can be partitioned into n disjoint subsets, they each having 2m minus 1 number of elements, and sum is this much, right? In at least n ways, n number of ways, and n is positive, by the way. Okay. So now so from the given matrix A, I will end up with the matrix B. Bi in fact, because there are many solutions, therefore I will denote it by B suffix I. And now this Bi is the first row with P. Don't forget this P. P is the label on the common edge. And if we add all the elements, it should be congruent to 0 with this P. Similarly, this entire row, if we add them, it should be congruent to 0. Similarly, this row should be congruent to 0, right? And yeah, now let me illustrate this idea. Since this is more abstract, so let me explain with this example. For that, I will consider 4 minus C4, the digraph. I mean, there are 4 copies of cycle C4. Here n is 4 and 2m, because m I have considered to be even, so I just put it as 2m equal to 4. And here p is the label on the common edge. I will fix that to be 7. And now this is the sum of the labels on the other edges of the cycle, and that should be add up to 21, right? And s is this set from 1 to 13, because there are 13 edges in this directed graph. And 7 is missing in this set because 7 is already fixed. I cannot use 7 again. Right? Now, this is the matrix. So I will put first n entries of this set in the first column, second n elements of this set in the second column, and next n elements, I mean 4 elements of this set in this third column. Right? And here 7 is missing. This column is totally different from these 2 columns. Okay. Now, we have to prove that the number of solutions, we have to find the number of solutions which add up to 21, including 1. And we can, that is x1 plus x2 plus x3 should be add up to 21. Here x1 can take the element from the first column, and x2 is from the second column, and x3 is from the third column, right? Okay. So now these are the solutions. So I have already mentioned that I use capital Nij for the number of solutions. So here N11, capital N11 is the number of solution including 1. Here we can see that the number of solution is 2. Similarly, the number of solution including 2. 2 is a part of this solution is 2 again. 3, number of solutions is 3, and so on. So we can see that N11 is 2, the number of solutions including 1. N12, I mean N12 is number of solutions with including 5, that is also 2. This is the one such solution, and this is another solution including 5, and so on. Here the minimum of Nij, if we look at it, is 2. Therefore, there are 2 ways we can partition the set into disjoint subsets so that it add up to 0, right? And now this is B1. So I forgot to mention the 7 in this row. I forgot to mention 7 is included in this column. 7 is fixed, the 4th column. So that add up to congruent to 0 modulo 14, right? So here is, I have mentioned here as C1.
Excuse me, Professor. You have only 5 minutes left.
Oh, okay. Thank you. Thanks for the reminder. Okay. So I will just complete this illustration and leave it. Okay. So this is C1. The first row add up to congruent to 0 modulo 14 and so on. And this is the corresponding graceful labeling of this 4 minus C4. Here 7 is fixed. This is 7 is fixed. And 1, 9, 11 is the elements of the first row. with one line 1, 9, 11 with this 7 add up to 0. And similarly 2, 6, 13, 7 is go to second copy of the cycle and it add up to 0. Similarly 3, 8, 10, 7 go to third copy, and 4, 5, 12, 7 go to the fourth copy of the cycle. And now the vertex labels are automatic. We can start with 0 here and we can keep filling according to the labels on the edges, right? So this is another solution for this diagram. So yeah, for even if M is odd, we partition the number in not this way. We just use the entries in the row wise instead of column wise. So that's the only difference. Okay, so I will stop here. Since time is up, I will stop here.
You have another 3 minutes if you want to continue.
Yeah, 3 minutes are there.
Yeah, thank you so much. So now, so this is which was asked by Jirimutu again in the year 2008 for odd n. Yeah, in the conjecture is for even n, but for odd n, can we whether the digraph is graceful or not? Still, this question is open. We don't know whether for every odd whether this digraph n minus cm is graceful or not. But at least we come up with an example where we can, even for odd n, we can come up with a graceful labeling. We just, by using the same idea, we just partition the set by using the system of simultaneous congruences, and we come up with this matrix, and this gives us the graceful labeling, and this actually labels the edges, and correspondingly one can find the labels on the vertices. So this is one example whether we can we find a graceful labeling for odd n. So for n equal to 7, there exists a graceful labeling. But for general n, odd n, we don't know whether the digraph is graceful or not. And yeah, so this is another conjecture which is made in 1994 by Du and Son. For any even positive even n and any integer m, whether the digraph n dot cm is graceful or not. I mean, here instead of putting the make edge to be common, here there are n copies of cycles with one common vertex. So we in fact prove more than this. We generalize this to the digraph d of n1 comma n2 etc nk, m1 comma m2 comma mk. Here this digraph, basically the structure of this digraph is there are n1 copies of cycle cm1, n2 copies of cycle cm2, etc. nk copies of cycle cmk. So we prove that this conjecture, this digraph is graceful, and we can see that this is a balanced digraph. The in degree and out degree of each vertex is same, therefore it is balanced. Therefore, the total number of edges must be even. Then only we can find a graceful labeling for this diagram. Now, these are the existing literatures on this conjecture, and we have proved this by using Friedlander results. And yeah, so let me quickly go through the illustration part. Here I have considered Z15 minus 0. We always go about the label on the edges, and this is how we consider all possible partitions, and we found the graceful labeling corresponding to each partition. So in this case, yeah, by using Friedlander results, we come up with the labels on the edges of each cycle, and we proved that the digraph is graceful. Here there are 3 copies of C3 and 1 copy of C5 with 1 common vertex, and it is graceful. So with this I will stop here, and these are some of the references. So yeah, if there are any questions from the participants, from the delegates, we can.
Professor Shiv Kumar?
Yes, sir.
Yes, there is one question from the participants.
Sure.
What is the necessary and sufficient condition for digraph with in-spoken unicycle wheel?
Oh yeah, it is quite natural, right? Let me go back to the diagram and we can. Even the necessary and sufficient condition is same. Why? Because if all edges are coming towards the central vertex, anyway, this we know that this B7 plus B, some of the labels on the edges of the rim should be congruent to 0, and the total number of edges is even. Therefore, even the sum of the labels on these spokes, or whether it is outspoken or inspoken, that should be congruent to 0. Even it is inspoken, that also should be congruent to 0 modulo 2n plus 1. Right? And if it is inspoken, then the congruence will change, there will be small change in the congruences, right? Because here it is, instead of A1 minus A0, we have A1 minus A0. Instead of that, we have A0 minus A1. That's the only change, right? There is no much change. The same partition will work, and we can prove that it is graceful.
Okay, thank you for answering, Professor Shivraj. There are no other questions from the participants, but if there are any questions from the panel members, you all can go ahead.
Yeah, I'd like to say something.
Yes.
It's a general suggestion for the participants mainly.
Yes, sir.
See, normally, as told by Shivraj Kumar, in graph labeling problems, we try to take the vertex values and give the values. Then we try whether we will be able to generate the edge numbers according to the set. So if you go through the paper, the directed graph case, it was published in very good journals. It's Siam Journal of Discrete Mathematics. See, they were not able to prove even for the wheel with 6 vertices. So, because at that time they tried using some other method. In a sense, normally we do trial and error method when we take the smaller graphs. So the thing is, Shivraj Kumar could solve this problem because we have approached through the other way. We thought, can we use throwing the edge labels and then using some theory, we can generate the vertex labels. So that is why those who are working on graph labelings, if they are not able to give the labelings, they should not leave. They should think that the tools which they have used is not correct one. So they should try to find some other tool so that they can solve the problem. They should be like that. In fact, this was a part of the project we did from DST, and just as I told earlier also, we have to comment, we have to appreciate, we have to compliment, like that. In fact, his thesis was reviewed by Professor Sinmin Lee and Professor Chaudham. So the Professor Chaudham, in his report, he said, after a long time, I am seeing such a quality thesis on graph labelings. This was a comment by Chaudham, and Professor Sinmin Lee said this thesis has to be given an award. And as mentioned during my introduction, Shivraj Kumar got the Best Paper Award in IIT Madras. I think it was the Research Scholars Conference.
Yes, sir. In National Meet of Research Scholars.
Like that. So if you do good work, then you can definitely publish such papers in good journals. So this paper was published in Graphs and Combinatorics. So with this, I compliment the speaker.
Thank you, sir.
For his good work.
Thank you, sir. Thank you so much.
I have just a little, see, when you consider it, the work is good, and
Thank you, madam.
I think graceful diagrams, very few people work on graceful diagrams. Now, when you take a wheel, okay,
yes,
you have a circle inside edges which you are calling spoke.
Yes,
then all the that is there is one vertex of degree, highest degree, which we call, let me call a central vertex.
Yes,
so central vertex may be out degree 0, in degree 0. Okay.
Yes,
you are considering these cases means you call it outspoke and inspoke.
Yes, ma'am.
Not outspoken.
Yes, ma'am. Yes, ma'am.
It should be outspoke. This is all the spokes have out degree. Inspoke means all the spokes are in degree. Means
okay.
It's not the outspoken becomes no, inspoken, outspoken.
Okay,
Just correct it.
In the introductory article.
Here you have written, nowhere you have written, it comes inspoke, outspoke. In this one, it comes outspoken. Therefore, participants have taken outspoken.
Okay, okay.
Madam,
it's a good work.
Thank you.
Madam, in his paper, actually, the definition, inspoken and outspoken, it is towards the center. So in this diagram, the spokes, the direction is from the center outside.
See, what happens basically in a diagram, there are two type of vertices. They have in degree and out degree. Okay. Yes. Out of in degree, we can have that is out degree 0, in degree 0. How you call it? Let me call in degree, out degree. The out, since that vertex is lies on the spoke. From there, all the spokes of the wheel go. So in spoke, out spoke, I would like that there all the spokes are out degree from that vertex. All the spokes are in degree coming to that one.
No,
excuse me, may I?
No problem.
Yes, Slavsky, yes.
May I add to that? I wrote the words in the chat. If you look in the chat, I think this is what Professor Acharya is saying.
I don't know.
Can you look at the chat?
He has worked on graceful diagrams. He has to see. I gave what I thought.
You wanted me to see the chart box?
Because we will say he's outspoken. What does it mean? Means he can criticize the people. He cannot take his own criticism. If I social system. Okay. Inspoken means you can keep on putting the arrows on his and he will be accepting everything.
Madam, actually, this we went by the original paper.
Exactly.
It was defined in the paper published by Bloom and Su.
Okay.
So we did not change the definition.
Yes.
They wanted to be outspoken that their work is good. No problem. Good. The work is good. I don't say just for the. I want to be very careful. To know from where the definition has come.
Okay. It's the language, right? This is about the language.
Yes, sir.
What can you show me the Bloom shoe paper in the references?
Okay, let me show it. Yeah.
Thank you. Okay.
Paper.
Oh, it is.
Yeah, this is the paper.
This one.
Siam Journal.
Graceful. Just let me write the problem. It is this is graceful diagrams and problem in network. This was the one.
No, not that.
Yeah, these are all.
The first paper.
On graceful directed graphs.
Yes, ma'am. If you want, I can share the paper with you.
Siam Journal of Discrete.
Professor Edda is having that article.
Sir, actually, earlier it was Siam Journal of Algebraic and Discrete Methods.
Yeah,
now it has been changed to Siam Journal of Discrete Mathematics.
Okay. No problem.
But it's available.
It is available.
I'm sorry. Go ahead.
No.
I wanted to ask about this matrix A.
Yes, sir.
Can we look at the matrix A? The general picture?
Wait a moment. I will.
Okay.
Yeah, sir, he will come, sir. There was some
that's
problem.
a great picture. Good picture.
Yeah, so where is it? Give me time sometimes. So.
That's okay.
Wait. Yeah. Yeah, at last I am able to.
There. Yes. Okay. So it seems that most of the columns, most of the entries are a row number plus a column number, right? So that like in the last column, the column number is 2m minus 2 times n, plus,
Yes,
and then there's a row number, 2, 3, 4, etc.
Yes, sir.
And there's some exceptional elements. If a matrix has all the row number, if every element is equal to a row number plus a column number, then what you can get a selection of the right numbers, the correct number of numbers that have the same sum by taking one from each row and column.
Yes, sir.
In any different way.
Yeah, in n number of ways we can choose it. So where n is positive.
N factorial ways.
But I don't think whether the sum of the elements should be added to this number. We have this restriction, right? You know, if you consider the number from each column, one entry from each column, so that it must add up to this number, 4mn into m minus 1 plus 4m plus n minus 2 divided by 2. That restriction.
I understand. But I'm talking, your matrix is not exactly the kind I'm talking about.
Okay.
There's a little difference because of your P. But
yes, exactly. P is missing. Yes.
Yes, suppose that P was not missing.
Yeah.
Just to consider this possibility.
Okay.
Then every single way of taking one from each row and one from each column is going to have the same sum automatically.
Okay.
And I wondered if you could use that in your modified matrix.
Yes.
To simplify getting the same sum.
I never tried because we cannot go for, you know, if we include P, then yeah, it will not give us the graceful labeling. So let us discard that idea.
Yeah, but you have to modify the idea, but there might be a possibility of using it to simplify the proof, maybe.
Okay.
Maybe not. It's only a thought. I don't know. You're the expert. I'm not an expert.
Okay, so I don't think. Let me check it out once. I will work it out.
Okay, I want to say a little bit more. A transversal. So is this a square matrix? I think it's not exactly a square matrix.
It need not be a square matrix. Yeah.
Okay.
Yeah.
So that's one problem.
Yes.
I see. So I was talking about a square matrix.
Because if m becomes larger and larger, then the square matrix will go last. Because if n is small and m is larger, then it need not be a square matrix.
That's right.
Yeah.
If it is a square matrix, then a transversal consists of taking one element from each row and column. So
exactly.
you don't.
I use that idea to prove that this digraph is graceful where m is odd.
Okay, I think that you know what I'm talking about, even though I'm not very clear. Okay, well, anyway, thank you. This is a clever method to use edge numbers first.
Yes.
I agree. Yes.
Yes.
Thank you.
Professor Shivraj?
Yes, sir.
Yes, there's one more question from the participants. I will just rephrase it. Why did you select the number of solution n equal to minimum of n suffix ij? Is it maximum?
Sorry, I can't hear you. Hello?
Okay, let me just repeat it. Why did you select the number of solution n equal to minimum of n suffix ij? Is it
Exactly.
maximum?
Yes, yes, great. No, here if I consider maximum, then yeah, I will go to the illustration. That way it is clear to all of what's it. If I consider the maximum, here suppose if here the maximum is 3, right? Can you hear me?
Yeah.
Yes.
Yeah, if I consider the maximum Nij to be maximum, then some of the entries with N11 it has only 2 solutions. N12 has only 2 solutions. Only N21 and other entries will have only 3 solutions, right? Then I will have a shortage, right? So with the rows, these are the only 2 solutions. For one and this one, it has 2 solutions. And even for 2, we have 2 solutions. But if I consider 3, then there exists no solution which is having 1. If I consider another matrix B3, if I call it, and now the number of solutions is only 2 for 1, right? And number of solutions for 2, 3, 4 is only 2. Therefore, I have to consider the minimum. If I consider the maximum, then I will be running shortage of the rows. That's the problem. That is why I consider the minimum.
Okay, well, I hope that answers the question of the participant. Are there any other questions from the panelist?
Yeah, if it is not clear, yeah, you can go through graphs and combinatorics. So it is written. Here I gave a brief idea, but there it is written in detail, so you can go through it.
Okay, thank you. Are there any other questions from the panelist?
Is this a long paper?
Yes, sir. It is quite lengthy paper.
Okay, I thought so. Yes.
Yeah, it is quite.
Jaslavsky sir. Hello.
Hello.
Tom,
Yeah.
I have today morning I sent you a copy of his thesis. You might have received.
Okay.
Yeah.
I will look. Thank you.
Yes.
Yeah, please go through it, sir.
Okay. I thank Professor Shivraj for this session, and I also thank Professor Adarsh K. Handa for chairing the session.
Yeah, thank you very much.
We come to an end of the morning sessions. We now break for lunch, and we will join back sharp at 2 o'clock for the afternoon sessions. I repeat, participants, please note, now we break for lunch, and we will join back sharp at 2 o'clock for the afternoon session. Professor Jessica, are there any other announcements?
No, that's it. So the attendance link will be shared for the evening session. So please be present. Yes, I think we can break for lunch.
Okay, have a nice appetite.
Yeah. Thank you, Zenford.
Thank